Good evening and welcome to The Sleepy Scientist. If you're listening to this, you've probably come here to wind down, to let your thoughts slow, your breathing settle, and your curiosity drift gently outward into the night. You're in the right place. Tonight's journey takes us far from the warmth of the inner planets, to a world that turned over long ago and never stood up again. Uranus, the tilted planet that rolls through space like a marble on its side, quietly defying the rules of the solar system. Now, before we get too far, let's address the elephant in the room, or rather the unfortunate name in the sky. Yes, Uranus, the planet that has caused centuries of schoolroom giggles. Astronomers have tried for years to keep a straight face about it, and mostly failed. But rest assured, tonight we'll keep things mature, mostly. Before we begin, I'd love to know where in the world you're listening from. It always amazes me to see how far these quiet journeys reach. From city apartments and country cottages to tiny rooms lit by starlight. So, if you'd like, share your location in the comments below. If you enjoy these calm explorations, please do give the video a like and subscribe to the channel. It really helps others find this peaceful corner of science. And to those who are already subscribed, thank you. Your support means the world. Please also click the notification bell so you won't miss the next quiet adventure we take together. I do hope this video isn't too interesting that it keeps you awake. But if it does, at least you'll drift off having learned something quietly wonderful about the universe. And if you enjoy anything and everything about space, you might also like my other channel, The Sleepy Astronomer, where we wander even deeper into the cosmos at an equally sleepy pace. The link is in the description. So settle in, relax, and let's begin tonight's exploration. What really happened to make a planet fall sideways? And how does a world like that still find its balance? Far beyond the reach of the sun's warmth lies a pale blue world that hardly anyone thinks about. Uranus drifts there, cold, silent, and slow. Their planet's so unusual it could almost be mistaken for a cosmic accident. Its tilt is so extreme that it doesn't spin like a top but rolls like a ball, turning its poles toward and away from the sun as it travels through its long 84-year orbit. Discovered in the late 1700s, Uranus was the first planet ever found through a telescope, the first to show humanity that the solar system wasn't finished yet. It broke astronomy wide open, proving there were still secrets hiding beyond the familiar glow of Saturn. And ever since that discovery, Uranus has been a riddle wrapped in blue haze, too far for regular study, too quiet for easy headlines, too strange to ignore. When the Voyager 2 spacecraft flew past in 1986, scientists expected swirling storms and vivid features like those seen on Jupiter and Neptune. Instead, they found a world of stillness, pale, almost featureless, as though time itself had slowed there. But beneath that calm surface lies a puzzle of ice, magnetism, and history. A world knocked over by some ancient disaster, still rolling along the edge of sunlight, indifferent to the passage of centuries. Tonight we'll drift through that mystery, from its discovery and naming, to its tilt, its seasons, its rings, and its quiet moons. We'll trace the clues that hint at a massive impact long ago, explore why it glows that gentle turquoise blue, and wonder what future missions might yet reveal. Uranus is often overlooked, yet it might hold the key to understanding a whole class of distant frozen worlds, not just in our solar system, but across the galaxy. So as you settle deeper into rest, listen closely. Beneath its calm exterior, Uranus has a story that's anything but ordinary. In the late 1700s, the universe felt smaller than it does today. The known planets, Mercury, Venus, Earth, Mars, Jupiter, and Saturn had been catalogued since ancient times. To most astronomers, the solar system seemed complete, tidy, and well-behaved. The outermost planet, Saturn, marked a kind of cosmic boundary. Beyond it lay only stars, or so everyone believed. But one man, with a homemade telescope and an unassuming garden observatory, was about to change that belief forever. His name was William Herschel, a German-born musician living in England, whose passion for stargazing was beginning to outshine his career as a composer. Herschel built his own telescopes from scratch, grinding mirrors by hand, polishing them under candlelight, and testing them in the cold night air. His instruments were some of the finest in the world, capable of revealing details never before seen. On the night of March 13th, 1781, Herschel was scanning the constellation of Gemini when he noticed a small, faint disk that didn't look quite like a star. It was slightly larger through the eyepiece, with a soft, fuzzy edge, something no star ever showed. At first he thought it might be a comet. That was the sensible conclusion. Comets were known to wander, and this object certainly seemed to be doing just that. Over the following nights, Herschel tracked its motion carefully. He recorded its position night after night, noting how it crept slowly across the background of fixed stars. Unlike a comet, though, it didn't sprout a tail or fade with time. It stayed bright, steady, and oddly planet-like. Herschel began to suspect that he had stumbled upon something far more significant than he had imagined. Word of his discovery spread quickly through the small but passionate world of 18th century astronomy. Other observers, intrigued by Herschel's meticulous notes, turned their telescopes toward the same region of sky. They confirmed what he saw. This was no comet. It moved in a nearly circular orbit far beyond Saturn. The mathematics told a clear story. This was a new planet. For the first time in human history, someone had found a world that no one had ever known existed. The impact of this realization was enormous. In one stroke, Herschel had doubled the size of the solar system as people understood it. Saturn was no longer the edge of creation. There was something beyond, something colder, dimmer, and vastly farther away. Astronomers began recalculating distances, revising tables, and redrawing the maps of the heavens. The orderly universe of classical astronomy suddenly became more mysterious. Imagine the wonder of it, standing in a candlelit study, ink staining your fingers, and realizing that the familiar planets, the ones named by Romans and observed by Galileo, were not the end of the story. The universe had just grown larger overnight, and all because one man decided to look a little closer at a star that didn't quite behave. At first, not everyone was convinced. Some astronomers doubted the claim, arguing that perhaps it was still a comet on a long circular path, but time, as it always does, settled the matter. Over the following months, careful measurements revealed that this object moved far too slowly and too precisely to be a comet. Its orbit was clear, regular, and planetary. Herschel had discovered a new world, the first since ancient times. He proposed naming it Georgium Sidus, or George's Star, in honour of his patron, King George III. It was, after all, polite to flatter royalty, if one hoped to secure funding for future telescopes. Many astronomers, however, were unimpressed by the idea of a planet named George. They preferred something more universal, a name that fit with Mercury, Venus, Mars, Jupiter, and Saturn. Eventually the name Uranus was chosen, after the ancient Greek god of the sky, the father of Saturn and the grandfather of Jupiter. The discovery was more than a moment of personal triumph. It marked a turning point in human understanding of the cosmos. For the first time, a planet had been found not through myth, chance, or naked-eye observation, but through the careful, methodical use of technology and measurement. The age of telescopic discovery had begun. Herschel became an overnight celebrity. King George rewarded him with a royal stipend, allowing him to leave his musical career and dedicate himself fully to astronomy. He went on to discover moons, nebulae, and even formulate ideas about the structure of the Milky Way. But nothing would ever quite compare to that first, quiet moment of realization that the faint dot in his eyepiece was a whole world waiting to be known. For astronomers of the time, Uranus was both a wonder and a puzzle. Its slow motion across the sky made it difficult to observe, and its dim light required the best telescopes to study. Still, its existence opened a door that could never again be closed. If there was a planet beyond Saturn, why not another beyond Uranus, and another beyond that? Within a few decades, that question would lead to the discovery of Neptune, and later Pluto. But all of it began with Herschel's patient observations and his refusal to ignore a star that moved when it shouldn't have. It's easy now, with our spacecraft and high-resolution telescopes, to forget how incredible that discovery truly was. In an era before photography, before computers, before electricity, one man and a hand-built telescope expanded the known universe. On that cold March night in 1781, the solar system grew wider, the sky a little deeper, and human imagination stretched just a little farther into the dark. One night, the sky quietly grew larger, and it's been expanding in our minds ever since. When William Herschel first realized he had discovered a new planet, he faced an unexpected challenge: what to call it. Naming a world was no small matter. Every planet known up to that point carried a name rooted in ancient mythology. Mercury, Venus, Mars, Jupiter, and Saturn. They had been recognized since antiquity, their titles passed down through centuries of stargazing and storytelling. But now there's this new member of the family, one never seen before, and tradition had not prepared anyone for what came next. Herschel, being both a scientist and a loyal Englishman, decided that a little royal flattery might be in order. He proposed calling the planet Georgium Sidus, or George's Star, in honour of King George III. It was the late 1700s, after all, and patronage could make or break an astronomer's livelihood. Naming the new planet after the monarch seemed like a noble gesture, a celestial thank you note for the funding and support Herschel hoped to receive. King George, naturally, was delighted. Astronomers across Britain, however, were less enthusiastic. Outside of England, the name did not exactly inspire reverence. French and German scientists in particular found it a bit absurd. Naming a planet after a mortal king, they argued, broke the elegant mythological symmetry that linked the heavens. It was as though someone had joined a pantheon of gods and declared, "This one's Steve." The debate soon spread through Europe's scientific circles. Should a planet be named for a human, or should it remain within the divine hierarchy of myth? Tradition had long tied celestial bodies to the deities of Greece and Rome, each chosen to reflect the planet's character. Mars for its red hue, Venus for its beauty, Jupiter for its grandeur. Saturn, slow and distant, was the elder god of time and harvest. The new planet, lying even farther from the sun, needed a name that fit that lineage, something timeless and appropriately majestic. The task of finding that name fell, unofficially, to a German astronomer named Johann Elert Bode. Bode was one of the first to recognize the importance of Herschel's discovery, and he believed that the name should align with mythological convention. Since Saturn was named after the Roman god who ruled over Jupiter's father, it made sense that the next planet outward should be named for Saturn's father. In Greek mythology, that figure was Uranus, the primordial god of the sky, born from chaos, who gave rise to the first generation of Titans. The logic was beautifully simple. If Jupiter was the king of the gods and Saturn his predecessor, then Uranus was the ancient sky itself, the source from which the others came. The lineage was complete, a divine family tree stretching outward through the solar system. It also had a quiet poetry to it. The newly discovered planet, pale and distant, named for the sky itself. It took several years for the name to catch on. In Britain, Herschel's Georgium Sidus lingered for a while, used mostly out of patriotism. In France, some preferred Herschel, honouring the discoverer himself. The French Academy of Sciences even voted to adopt that name for official use, at least for a time. But slowly, steadily, Uranus began to win. It was the only name that fit both scientifically and symbolically. Grand without being self-serving, mythological without being redundant. By the early 1800s, most astronomers across Europe had accepted Uranus as the planet's true name. Herschel himself, though fond of his royal dedication, eventually yielded to the tide of tradition. In hindsight, it was probably for the best. A planet called George might have sounded somewhat less majestic, orbiting alongside Jupiter and Saturn. Still, the name Uranus has had a complicated legacy. The pronunciation alone has caused more mischief than any other in astronomy. For more than 2 centuries, school teachers and science communicators have done linguistic gymnastics to avoid giggles. Some pronounce it Y-O-O-R-U-H-N-U-S, others Y-O-O-R-U-H-N-A-H-S, and a few valiantly attempt O-O-R-A-H-N-O-O-S to match the original Greek. Regardless of pronunciation, the humour has endured. Herschel could never have imagined that his noble discovery would one day be the butt of so many jokes, quite literally. Beneath the jokes, though, lies something meaningful. The act of naming in science has always been a form of reverence, an attempt to give identity to mystery. To name a world is to acknowledge it, to bring it into the story of human understanding. When astronomers named Uranus, they weren't just labelling a distant sphere of ice and gas. They were placing it within the great myth of the sky itself, connecting human imagination to cosmic reality. The choice of Uranus carries a subtle beauty. In Greek mythology, Uranus represented the heavens, vast, eternal, unchanging. He was both the father of the gods and the embodiment of the sky. Naming the planet after him felt almost like an act of cosmic symmetry. The sky god given form in the actual sky. It was as if the ancients had whispered forward through time, and modern science had finally answered. It also signalled a shift in how humanity viewed the universe. Until Herschel's discovery, the planets were a closed set, defined by what could be seen with the naked eye. Their names belong to a mythic past, to a time when the heavens were ruled by stories rather than science. Uranus bridged that gap, the first planet discovered through technology, yet still named through myth. It was both modern and ancient, empirical and poetic, human and divine. That duality is what makes the name so fitting. It reminds us that science doesn't erase wonder, it deepens it. Even in an age of telescopes and mathematics, we still reach for mythology to describe what we find. There is something timeless about that. something comforting in the thought that the same human impulse that once invented gods still drives us to explore the stars. Over the centuries, the name Uranus has become more than a word. It has become a symbol of curiosity itself, of how discovery stretches language, imagination, and culture. It stands as a quiet tribute to all the unknowns waiting in the dark and to the human need to give them meaning. When you look up at the faint blue point of Uranus in the night sky, you're not just seeing a distant planet. You're seeing a name that connects two worlds, the mythic heavens of the ancients and the scientific cosmos of today. Fitting, perhaps, that the sky itself would be named after the heaven's first father, a reminder that even in the age of reason, the universe still speaks in the language of myth. Among all the planets that orbit the Sun, only one seems to have taken the phrase thinking outside the box a little too literally. While every other planet spins more or less upright, Uranus decided to lie down. Its axis is tilted by an astonishing 98 degrees, which means it doesn't just spin, it rolls. Imagine a marble lazily turning on its side as it circles the Sun, its poles where its equator should be. That's Uranus, the cosmic oddball forever doing its own thing. To put that in perspective, Earth's axial tilt is about 23.5 degrees, just enough to give us our seasons. When our planet leans slightly toward the Sun, we get summer. When it leans away, we get winter. Saturn tilts a little more, Mars a little less, but all of them rotate in roughly the same orientation, like spinning tops all standing on the same table. Uranus, on the other hand, is the top that has fallen over and just kept spinning anyway. No one knows exactly how Uranus ended up in such an extraordinary position, but the leading theory points to a colossal collision billions of years ago, sometime during the early chaos of the solar system's youth. In those days, space was crowded with leftover debris from planet formation, massive objects the size of moons or even small planets, all hurtling around in unstable orbits. It was an era of frequent and violent impacts. One such wandering body may have slammed into Uranus at just the right or wrong angle, knocking the entire planet onto its side. The evidence for such a cataclysm hides within the details of Uranus's structure and motion. Its moons all orbit in the same tilted plane as the planet's equator, suggesting they formed or were reshaped after the Great Collision. Its magnetic field, strangely skewed and off-center, may also trace back to that ancient trauma. And then there's the tilt itself, far too extreme to have happened gradually. The simplest explanation remains that Uranus once stood tall and proud, until something big hit it hard enough to change its destiny forever. The idea is almost cinematic. Two newborn planets colliding in slow motion, their surfaces liquefying from the force, the wreckage reforming into something new. In the aftermath, Uranus would have stabilized into its sideways orientation, its atmosphere settling and its moons gathering from the debris. The cosmic billiard game that created our solar system left this one world permanently crooked. Whatever the cause, the result is spectacularly strange. Because Uranus is tilted so far, its poles point almost directly at the Sun for decades at a time. For roughly 21 years, one half of the planet basks in continuous daylight while the other is locked in darkness. Then, as Uranus continues its slow 84-year orbit, the situation reverses. A single year on Uranus spans nearly a human lifetime, and each season lasts about 21 Earth years. If you lived there and had the patience of a glacier, you could experience a sunrise that takes decades to complete. This sideways rotation also makes for peculiar day-to-day lighting. Near the equator, sunlight sweeps in from a bizarre angle, casting long shadows and painting the atmosphere in glancing blues and greens. Near the poles, the sun can hang motionless in the sky for years, drifting in lazy circles as the planet rolls along its path. It's not a world where you check the time by looking at the sun. It would either never rise or never set. The extreme tilt also gives Uranus its unpredictable weather patterns. Despite its calm appearance, its atmosphere experiences odd seasonal shifts. When one hemisphere finally turns away from the sun after 2 decades of light, the sudden temperature change can stir massive methane storms and jet streams that move faster than any wind on Earth. It's as though the planet spends years quietly charging its energy, then releases it in a brief chaotic outburst before falling silent again. Even Uranus's magnetic field doesn't play by the rules. On Earth, the magnetic poles roughly align with the geographic poles. Our compass needles point north because the magnetic field follows the planet's spin. But on Uranus, the magnetic axis is tilted about 60 degrees from its rotational axis, and it doesn't even pass through the planet's centre. This offset creates a magnetic field that wobbles and tumbles as Uranus rolls, producing a magnetosphere that's unlike anything else in the solar system. Scientists believe that this too may be a result of that ancient collision, which could have shifted or distorted the planet's internal layers. For its moons, the tilt creates an entirely different rhythm of existence. Most of them orbit within Uranus's equatorial plane, which means they too are tipped sideways relative to the Sun. As Uranus rolls, its moons experience the same long seasons of light and shadow. Imagine a moon where the sun rises once every 42 Earth years, or where half the sky glows softly blue for decades while the other half sleeps in darkness. The gravitational effects of this tilt also make their orbits slightly warped and irregular, a subtle echo of the chaos that shaped them. It's strange to think how a single event billions of years ago could ripple forward through time in so many ways. That one violent impact didn't just change the planet's orientation, it rewrote everything about its character, its magnetism, its climate, its moons, even its identity as an ice giant, all shaped by that one colossal nudge. What might have been an ordinary world became a sideways one, a cosmic outlier rolling through the dark. Some astronomers have suggested that the tilt could have developed more gradually, through gravitational interactions with a giant moon that no longer exists. Over millions of years, such a moon might have slowly destabilized Uranus's rotation until it toppled over. Eventually, the moon itself could have been torn apart by tidal forces, its fragments forming the planet's faint rings and small satellites. Whether through sudden violence or slow evolution, the outcome remains the same. Uranus is forever off balance, forever unique. There's something quietly poetic about that. In a solar system built on predictable motions, planets spinning neatly like clockwork toys, Uranus is the exception that reminds us how fragile order can be. A single cosmic accident billions of years ago still dictates the rhythm of its days and nights, its seasons and storms. It is in every sense a planet caught mid-tumble. If you could watch the solar system from above, you'd see all the planets circling the sun in roughly the same flat disk. They tilt slightly, they wobble a bit, but their north poles generally point in the same direction, all except one. Uranus spins like a wheel rolling along its track, its poles tracing a circle in space. From that distant vantage, it must look like a dream that forgot which way was up. Despite its unusual orientation, Uranus remains remarkably stable. Its axial tilt doesn't seem to drift or wobble much over time, suggesting that whatever happened in its past has long since settled. It rolls with Quiet confidence, as if it has accepted its odd fate. There's no sign it's trying to straighten up, no cosmic attempt to fit in with the rest. It simply turns, slowly and gracefully, sideways through eternity. And perhaps that's part of its charm. In a universe that values symmetry, Uranus is a reminder that beauty often lies in imperfection. A planet that fell over billions of years ago still holds its place in the grand dance of the solar system, steady in its imbalance. Not broken, not wrong, just different. A world forever tilted, forever unique. A planet that tumbled once and never bothered to stand again. Time behaves differently on Uranus, not in the way Einstein might have described it. There's no relativity trick or time dilation here, but in a slower, quieter sense. On this pale blue world, the rhythm of a light and dark stretches so far beyond human experience that it almost feels like another dimension. Where Earth hurries through its days and seasons, Uranus drifts. Its orbit around the Sun takes 84 Earth years to complete, which means that a single year on Uranus could last an entire human lifetime. Because of its 98-degree tilt, this long orbit produces some of the strangest seasons in the solar system. On Earth, our planet leans modestly, giving each hemisphere its turn in sunlight and shadow over the course of a year. On Uranus, that same principle plays out on a staggering scale. When one of its poles tilts toward the Sun, it stays illuminated for 21 years. The opposite pole, meanwhile, is plunged into an equally long night. Then, after more than 2 decades of near constant daylight or darkness, the planet slowly rolls over, reversing the situation. It's difficult to imagine what that would look like from the surface, if there were a surface to stand on. For 21 years, the Sun would hang motionless in the sky, circling slowly around the horizon but never setting. The light would be dim and distant, filtered through a haze of methane and thin clouds, yet it would persist for decades without relief. Then, one day, after a generation of endless day, the Sun would begin to sink. It would touch the horizon and fade below it, not for an evening, but for a season that lasts nearly a quarter of a century. The planet's pole would fall into darkness, illuminated only by the faint aquamarine glow of scattered sunlight reflecting from its rings. Meanwhile, along the equator, time plays a different game. There, the Sun rises and sets in something closer to a daily rhythm, but the light angles are strange and shifting. During the long Uranian year, the equator experiences 2 great equinoxes, moments when the Sun shines directly on its middle regions, and the boundary between light and dark runs neatly across the planet's surface. These are fleeting, delicate times. As the Sun's light grazes the rings, they cast sweeping shadows over the atmosphere, stretching like dark lines across the glowing blue clouds. The planet's day and night become balanced for a short while, before the tilt continues and balance is lost again. Those equinox periods occur only twice per Uranian year, roughly once every 42 Earth years. The last one happened in 2007, when telescopes captured the ghostly image of its ring shadows slicing across the planet's pale face. The next won't come until around 2049. For astronomers, these moments are rare and precious. The angle of light changes the way the atmosphere behaves, revealing patterns and structures invisible at other times. The planet seems to wake briefly, stirring from its long twilight before drifting back into stillness. Because of this slow-motion orbit, time on Uranus is best described not in hours or days, but in ages. A single day there lasts just under 17 hours, but the planet's tilted spin means that concept barely applies. Near the poles, a day is meaningless. The sun never sets or never rises for years at a stretch. Near the equator, the alternation between day and night feels disjointed, stretched, and oddly sluggish. If you were somehow living on a moon orbiting Uranus, your calendar would be less about days and more about generations of light and dark. For scientists, this bizarre cycle poses intriguing questions. The long exposure to sunlight at one pole, followed by 2 decades of cold darkness, likely drives massive, slow-moving weather patterns deep within the atmosphere. Methane, which makes up much of Uranus's upper atmosphere, freezes out and sublimates in enormous seasonal shifts. These changes happen on a scale so long that no human mission has ever been able to observe them directly from start to finish. Every glimpse we have is a brief snapshot in an 84-year film reel that we've only seen a few frames of. Imagine trying to understand Earth's climate by watching for a single week every 50 years. That's roughly our level of insight into Uranus's seasons. We've only seen one pole lit in detail, and we're still waiting for the opposite hemisphere to fully face the sun again so we can compare them. The planet's weather could be profoundly asymmetrical, but for now, that remains one of its many quiet mysteries. There's also something fascinatingly symbolic about its sideways relationship with time. Most planets turn upright enough that their cycles make intuitive sense to us. Day, night, season, year. On Uranus, those divisions blur. Time doesn't tick so much as drift, measured by the slow lean of a world rolling endlessly through space. The familiar rhythm of light and dark, the pulse that governs life on Earth, becomes stretched until it almost breaks. From afar, you might expect such a slow rotation around the sun to make Uranus a place of total stillness, but in reality, its tilted orbit creates subtle yet dramatic transitions. When one hemisphere finally begins to fade from its decades-long day into night, sunlight grazes the atmosphere at strange angles, igniting soft pastel bands and faint streaks across the clouds. Then the light fades completely, and for the next 21 years, that hemisphere faces the cold of space, warmed only by faint infrared radiation from the other side. It's worth remembering that even at its brightest, sunlight on Uranus is feeble. The planet is so far from the sun, nearly 3 billion kilometers away, that daylight there is no brighter than a deep earthly twilight. Even during its long summer days, the sky would never blaze. It would glow softly like light through fog. So when night finally comes, the contrast isn't sharp. The darkness is gentle, endless, and strangely serene. If you could hover above Uranus during one of its equinoxes, you'd see the planet half in sunlight, half in shadow, turning slowly as its rings cast thin, dark arcs across the bright blue haze. The effect would be haunting. A planet caught between worlds, illuminated yet half asleep. The light itself would change colour as it passed through different layers of the atmosphere, fading from white to turquoise to a dusky, almost grey-blue. The scene would shift so slowly that you could watch it for hours and barely notice movement. Time, as far as the human mind is concerned, would seem to stand still. The moons that orbit Uranus experience this strange passage of time as well. Each one rolls along the planet's tilted equatorial plane, following it through its seasons. For decades, one side of a moon may face constant sunlight, baking under the dim warmth, while the other remains locked in frozen shadow. When the seasons reverse, those same moons are slowly bathed in light again, their icy surfaces gleaming like mirrors in the faint glow. It's an intricate ballet of illumination. each moon a participant in the planet's long sideways dance. Because these cycles unfold so slowly, we may never fully witness them within a single human lifetime. Our brief observations, spread across decades, can only hint at the grandeur of a world where sunrise and sunset are decades apart. For Uranus, change is glacial, not in the sense of ice sheets sliding across continents, but in its sheer patience. It has waited through billions of such cycles, rolling on its side in quiet defiance of celestial norms. Perhaps that's part of the planet's enduring mystery. In a solar system that moves with clockwork precision, Uranus refuses to hurry. It teaches in its own frozen way that time can stretch, bend, and soften, that even in the coldest reaches of space, patience is its own kind of beauty. On Uranus, there is no quick transition from dawn to dusk, no daily rush of time. Instead, light lingers and darkness waits. Decades of day drift into decades of night, and the planet rolls gently onward, unbothered by the pace of the sun. On Uranus, sunrise and sunset are decades apart, and the sky never seems in any hurry to choose between them. Uranus belongs to a rare and curious category of planet, an ice giant. That phrase sounds dramatic, almost like something out of mythology, but it's a real scientific term. Within our solar system there are 4 gas or ice giants: Jupiter, Saturn, Uranus and Neptune. Yet these worlds, though they all loom large and remote, are not the same. Jupiter and Saturn are the gas giants, massive swollen spheres of hydrogen and helium, their bulk made of the same material as stars. Uranus and Neptune, by contrast, belong to a different class. They are smaller, denser, and made mostly of substances that would freeze into solids or liquids under normal conditions. Water, ammonia, methane. These are the ice giants, planets built from the frozen chemistry of the outer solar system. It's worth saying that ice here doesn't mean what it does on Earth. There are no glaciers glinting in the sunlight or frozen lakes waiting for alien skaters. The temperatures and pressures inside Uranus are so extreme that the word ice simply describes volatile molecules trapped in dense, exotic forms. Water, methane, and ammonia behave more like thick, pressurized fluids than the frozen crystals we know. Yet those compounds dominate Uranus's makeup, giving it a unique internal structure that differs dramatically from its larger cousins closer to the Sun. Imagine slicing Uranus in half to see what lies within. The outermost layer is a thin gaseous shell made primarily of hydrogen and helium, the same light gases that make up most of the Sun. This layer is only a small fraction of the planet's total mass, yet it forms the misty blue atmosphere we see. Beneath it lies an immense mantle of water, ammonia and methane ices, compressed into hot, dense fluids by the weight of everything above. Deeper still, near the centre, is a rocky core, a mixture of silicates and metals that may not be solid in the familiar sense, but instead a compact sphere of dense, molten rock under unimaginable pressure. This internal layering makes Uranus unlike any other world in the solar system. Its outer atmosphere merges gradually into its icy mantle, without the clear boundaries we see on Earth. There's no surface where you could stand, only a slow, crushing descent through increasingly alien material until you reach the planet's deep interior. Pressure increases by millions of times what we experience at sea level, and temperatures soar far above anything survivable. Yet even with all that heat trapped inside, Uranus remains astonishingly cold. In fact, Uranus is the coldest planet in the solar system. Despite orbiting closer to the Sun than Neptune, its cloud tops measure around -224 degrees Celsius. That's colder than any natural place we've measured anywhere. It's also a puzzle, because most planets radiate more heat than they receive from the Sun. Jupiter and Saturn, for instance, glow in infrared light as they release leftover heat from their formation. Neptune, too, emits almost twice as much energy as it absorbs. But Uranus, practically nothing. It sits there, silent and dim, giving off no detectable warmth at all. No one is entirely sure why. One possibility is that the same colossal impact that knocked the planet onto its side billions of years ago also disrupted its internal heat flow. Perhaps the crash mixed up the layers inside Uranus, creating an insulating shell that trapped warmth at depth and prevented it from escaping. Another theory suggests that its composition might allow heat to escape only slowly, locked behind layers of dense conductive ices. Or maybe, long ago, it simply radiated most of its internal energy into space and never regained it. Whatever the reason, the result is a planet that seems frozen not just in temperature, but in temperament, quiet, still, and self-contained. The materials that make up Uranus's mantle are unlike anything we can reproduce on Earth. But scientists have tried. In laboratory experiments, researchers compress water and ammonia under tremendous pressures using diamond-tipped anvils and powerful lasers. What they observe is extraordinary. Under such extreme conditions, water stops behaving like an ordinary liquid or solid and becomes something in between, a phase known as supersonic water. In this form, oxygen atoms lock into a lattice while hydrogen ions move freely through it, almost like electricity flowing through metal. It's a substance that's part solid, part liquid, and entirely alien. Supersonic water could explain many of Uranus's mysteries. Because it conducts electricity, it might generate part of the planet's magnetic field, one that's tilted, offset, and unpredictable compared to Earth's. It could also account for the planet's internal layering, acting as a barrier between the gaseous atmosphere above and the rocky core below. If this material really exists inside Uranus, it would mean that the planet's heart is literally alive with electrical currents, a deep ocean of glowing conductive ice swirling around a hidden core. It's almost poetic to imagine, deep within a world that appears frozen and silent, there may be a restless sea of energy moving unseen. The paradox of Uranus is that it is both motionless and dynamic, calm on the outside, chaotic within. Its slow clouds drift gently, concealing a complex interior of pressures and temperatures so high that common materials behave in unearthly ways. Even the simple molecules that make up its air, hydrogen, helium, and methane, tell a quiet story. Methane absorbs red light, reflecting the planet's now famous turquoise hue. It also forms delicate clouds in the upper atmosphere, where temperatures are cold enough for methane to condense into crystals. These high-altitude mists drift through layers of gas that grow denser and darker with depth, gradually merging into that mysterious ocean of icy fluid far below. The deeper you imagine falling through Uranus, the stranger it becomes. Somewhere beneath the clouds, the atmosphere thickens into a compressing fog, and then into a heavy, slushy mixture of exotic chemicals. The pressure climbs to millions of atmospheres. Water, ammonia, and methane lose their familiar forms, fusing into something halfway between liquid and solid. And at the heart of it all, buried under tens of thousands of kilometers of alien chemistry, the rocky core sits quietly, perhaps no larger than Earth, perhaps smaller, surrounded by an ocean that never freezes and never melts. Scientists have long wondered how stable such a world can be. Without internal heat to churn its atmosphere, Uranus seems locked in stillness. Its magnetic field, generated somewhere in that slushy mantle, drifts and twists unpredictably. Yet on the surface everything appears calm. The clouds move sluggishly, the colours fade gently into one another, and even the storms that sometimes flicker across the planet seem subdued compared to those on other giants. It's as if all the turbulence has retreated inward, hidden from view behind a serene blue mask. In many ways, Uranus represents a boundary in our understanding of planets. It's the halfway point between the gas giants and the rocky worlds, the place where familiar elements behave in ways that defy our intuition. It reminds us that ice and rock and gas are not absolute states, but labels we assign to materials under earthly conditions. In the crushing depths of Uranus, those categories dissolve. Water becomes metal, gas becomes fluid, and ice flows like molten glass. Our knowledge of Uranus's interior remains mostly theoretical, built on indirect measurements of gravity, magnetism, and density. We have never sent a probe into its atmosphere, never watched it up close beyond a brief flyby. But even from afar we can sense its quiet presence, a frozen giant spinning slowly through the dark, keeping its secrets deep inside. If the solar system has a place of stillness, it's here. In this cold, pale world, time and heat seem to have stopped. Uranus turns on its side, rolls through the shadows, and keeps its heart hidden beneath layers of frozen calm. Yet inside that silence may lie one of the strangest oceans in existence. A sea not of water, but of something far more extraordinary. The restless glowing ice at the centre of a planet that forgot how to burn. In most of the solar system, magnetic fields behave themselves. They rise from deep within a planet's core, align roughly with its axis of rotation, and produce a steady, predictable shield that guides charged particles in elegant arcs. Earth's magnetic field, for example, is like a tidy bar magnet running through its centre, tilted only slightly from the planet's spin. Jupiter's is vast but equally disciplined, wrapping its enormous body in an orderly cocoon of radiation. But then there's Uranus, the rebel of magnetism, the planet whose invisible forces seem to have rolled over right alongside its tilted body. When Voyager 2 arrived in 1986, scientists expected to find something roughly similar to what they'd seen at other planets. A magnetic field centered around the core, tilted maybe a few degrees, with clean patterns and well-behaved lines. What they found instead was a mess. The magnetic field of Uranus wasn't simply tilted, it was completely misaligned, offset from the planet's centre by more than a third of its radius, and angled at nearly 60 degrees from its rotational axis. Nothing lined up. The geometry was lopsided, the poles were nowhere near where they should have been, and the data made even the most experienced physicists scratch their heads. This bizarre configuration means that Uranus's magnetic field doesn't just sit still and rotate neatly with the planet. Instead, as Uranus rolls along its orbit, the entire magnetosphere, the region dominated by its magnetic field, tumbles and wobbles through space. Imagine holding a flashlight that's not centered in your hand and spinning it while walking in circles. The beam would sweep and twist unpredictably, sometimes pointing outward, sometimes inward, sometimes almost turning back on itself. That's roughly what Uranus's magnetic bubble does as it moves through the solar wind. The source of this magnetic confusion lies deep within the planet itself. On Earth, magnetism comes from a molten iron core where convection currents of liquid metal act like an enormous dynamo. The movement of electrically conductive material creates a stable magnetic field that aligns with the planet's spin. But Uranus is different. It doesn't have a metallic core in the same way Earth does. Instead, its magnetic field seems to be generated within its thick, slushy mantle, that strange mixture of water, ammonia, and methane under immense pressure. This mantle behaves neither like a solid nor a liquid, but something in between. Deep within it, some scientists suspect lies the mysterious state known as superionic water, where hydrogen ions drift freely through a lattice of oxygen atoms, allowing electricity to flow. It's this electrically active region that likely powers Uranus's magnetic field. But because it's located far from the planet's center and shaped by uneven layers, the field it produces is crooked, incomplete, and constantly shifting. It's as if Uranus built a dynamo, forgot to center it, and then decided it was fine anyway. The result is one of the most chaotic magnetospheres in the solar system. The magnetic poles of Uranus wander wildly relative to its surface, sometimes pointing almost sideways, sometimes backward, depending on where the planet is in its rotation. As Uranus spins, lying on its side like a rolling barrel, the magnetic field tilts and sweeps through space in enormous loops. Every 17 hours, the entire magnetosphere essentially flips, exposing one side to the solar wind and then the other. No other planet does anything quite like it. For Voyager 2, which flew past Uranus for only a few short hours, this magnetic dance made data collection a nightmare. Instruments that normally measured steady patterns of charged particles found themselves facing wildly varying signals. Magnetic field lines twisted in unexpected directions. At times, the reading suggested that the planet's magnetic tail, the long stretch of field lines that trail behind it, wasn't even pointing away from the Sun, as it does on Earth and Jupiter. Instead, it spiraled, corkscrew-like, through space, twisting and turning as Uranus rotated. It was a magnetic labyrinth, unpredictable and beautiful in its defiance of order. This peculiar field has some remarkable consequences. For one, it means that Uranus's auroras, the glowing curtains of light created when charged particles strike the atmosphere, appear in unusual places. On Earth, auroras cluster near the magnetic poles, giving us the northern and southern lights. On Uranus, those poles are so far from the geographic ones that auroras can appear at strange latitudes, sometimes almost around the planet's equator. They flicker faintly in ultraviolet light, invisible to the human eye but recorded by telescopes orbiting above Earth. It also means that the planet's magnetic field offers little consistency as a shield. Most magnetospheres deflect the solar wind, a stream of charged particles from the Sun, in predictable ways. On Uranus, the shield is constantly changing shape, sometimes strengthening, sometimes weakening, depending on how the planet happens to be oriented at that moment. Some days its magnetic field might protect it well. Other days it may open gaps where solar particles can rush in and interact directly with the atmosphere. The planet's sideways rotation means that every day of Uranus brings a completely new magnetic configuration. For scientists studying planetary magnetism, Uranus is a puzzle wrapped in turquoise clouds. Its magnetic field challenges the assumptions that magnetic dynamos must be symmetric or centered. It also forces researchers to rethink how fluid layers behave under extreme conditions. What happens when the generator of a magnetic field isn't made of metal, but of exotic ices under crushing pressure? How does a planet maintain such a field for billions of years when it seems so off balance? Somehow Uranus manages it, a magnetic field as steady in strength as it is wild in geometry. One theory suggests that the offset field could be the result of multiple layers within the mantle, each generating its own partial magnetic contribution. If those layers are not perfectly aligned, the combined field would tilt, distort, and drift, exactly what we observe. Another idea points back to the ancient collision that knocked Uranus onto its side. That impact may have scrambled the planet's internal symmetry, leaving the magnetic generator permanently displaced. If true, Uranus's magnetism would be a literal echo of that primordial event, an invisible scar still rippling through space. Despite its oddity, the magnetic field of Uranus is not weak. In fact, it's roughly as strong as Earth's, though stretched into a much larger shape by the surrounding plasma and solar wind. Voyager's instruments detected a magnetotail, the elongated region of magnetic influence extending away from the Sun, that twisted into a long, curling helix millions of kilometers long. It was as though the planet's invisible wake were writhing like a ribbon in a slow cosmic breeze. From a poetic standpoint, it feels appropriate that Uranus's magnetism should refuse to behave. This is, after all, the planet that spins sideways, the planet whose seasons last for decades, the planet that broke every rule of celestial alignment. Even its invisible forces lean sideways, caught forever in the same cosmic tumble as the rest of the world. Its magnetosphere isn't a tidy shield, but a living, shifting shape, a field of motion as dynamic as the planet's own improbable tilt. If we could see it with human eyes, Uranus's magnetic field would look like an enormous transparent cocoon that flickers and warps as the planet rolls. It would shimmer with energy as solar particles spiral along its distorted lines, forming faint auroral glows that dance in unexpected places. Every rotation would twist that cocoon, sending waves of charged particles curling outward like ripples from a sideways stone thrown into the solar wind. The more we study Uranus's magnetism, the clearer it becomes that no single pattern defines it. Instead, it's an evolving system, shaped by fluid movement, rotation, and tilt, unpredictable yet consistent in its persistence. It's a reminder that nature often prefers a symmetry, that even in the realm of physics there's room for eccentricity. And so Uranus drifts on, rolling through the dark with its tilted magnetic heart glowing unseen beneath its clouds. Where other planets align neatly with their invisible compasses, Uranus continues to spin askew, its field flipping, wobbling and spiraling in a graceful, endless dance. At first glance, Uranus looks like a planet that has nothing to say. Through a telescope, it appears as a smooth, pale blue-green disk, almost perfectly uniform, with no bold storms, no colourful bands, no swirling tempests like those seen on Jupiter or Saturn. To early observers, it must have seemed almost artificial, as if someone had painted a turquoise marble and hung it in space. Even today, with the power of the Hubble Space Telescope and the sharp eyes of spacecraft, Uranus remains eerily calm. It is by nearly every measure the quietest atmosphere in the solar system. This stillness is deceptive, though, because Uranus is far from simple. Its calm exterior hides deep physics, strange chemistry, and a balance unlike anything on the other planets. To understand why it appears so peaceful, we have to look at its energy, or more accurately its lack of it. Every planet, including Earth, glows faintly in infrared light, radiating more energy into space than it receives from the Sun. That glow is the leftover heat from its formation, a sign that deep within, the planet is still cooling and releasing stored energy from its violent birth. Jupiter and Saturn, for example, shine with internal warmth. They're still contracting slowly under their own gravity, converting potential energy into heat. Neptune too radiates nearly twice the energy it receives from the Sun, its internal furnace still quietly burning billions of years after the solar system formed. Uranus, however, does not. It is the only major planet that shows no measurable excess of internal heat. Its energy output matches almost perfectly the sunlight that falls upon it. Whatever warmth it once had seems to have vanished. The result is an atmosphere frozen in equilibrium, a world so thermally balanced that there's barely enough movement to stir its clouds. Why this happened remains one of planetary science's unsolved mysteries. One idea is that the same catastrophic impact that knocked Uranus onto its side billions of years ago also disrupted its interior layers, creating an insulating shell that trapped the remaining heat deep inside. Another suggests that the planet may have formed differently from Neptune, losing its energy more efficiently during its early years. Whatever the cause, the outcome is striking. Uranus radiates less heat per square meter than any other planet in the solar system. It's not just cold in temperature, it's cold in spirit. At the cloud tops, temperatures hover around -224 degrees Celsius, close to the theoretical minimum for a planet receiving sunlight from that distance. The air is a blend of hydrogen, helium and methane, the latter giving Uranus its signature blue-green hue by absorbing red light. The upper atmosphere is thin and translucent, with faint layers of haze and high clouds made of methane crystals. These clouds drift gently across the planet, moving so slowly that they barely leave a mark. There are, however, occasional exceptions to this calm. Every so often, bright spots appear in Uranus's atmosphere, towering methane clouds that rise higher than usual, catching sunlight like pale sparks against the turquoise backdrop. These storms, though rare, remind scientists that the planet is not entirely asleep. Most seem to occur near its equinoxes, when sunlight shifts from one hemisphere to the other, perhaps triggering subtle changes in atmospheric circulation. But even at their most dramatic, these storms are faint echoes compared to the roaring tempests of Jupiter's Great Red Spot or the supersonic winds of Neptune. When Voyager 2 flew past Uranus in 1986, scientists were astonished by how little it saw. Every other gas or ice giant revealed layers of structure, belts, zones, or whirlpools. Uranus showed almost none. The spacecraft's cameras struggled to find any contrast at all. What little texture appeared had to be enhanced by stretching the images beyond their normal limits. To the human eye, the planet was almost featureless, a glowing, serene orb suspended in deep space. For decades, that image defined Uranus, the quiet one, the subdued sibling of the outer planets. It wasn't until much later, when better telescopes and infrared sensors became available, that scientists began to see hints of activity. Beneath the calm, there are narrow jet streams, subtle temperature gradients, and faint cloud bands that emerge only under certain lighting. These structures suggest that Uranus's atmosphere is not completely stagnant but moves with a slow, stately rhythm. It breathes, but softly. This gentleness extends to its winds which, while still reaching hundreds of kilometers per hour, are far weaker than those on Neptune or Jupiter when scaled to their environments. In planetary terms, Uranus's atmosphere is balanced on a knife edge. Too little internal heat to drive chaotic storms, too much stability to collapse into stillness entirely. It occupies a kind of perfect calm, where the forces of convection, radiation, and chemistry all seem to hold one another in quiet compromise. To many scientists, this balance is as fascinating as the chaos of other planets. It demonstrates what happens when a world reaches thermal peace, when its interior stops feeding energy to its skies. On Uranus, weather becomes geometry, faint lines, soft gradients, and occasional dots of brighter methane frost. It's as though nature itself decided to experiment with minimalism, a planet as smooth as an idea. Yet this serenity also makes Uranus a challenge to study. Its lack of features gives few clues about wind speeds or atmospheric composition. The storms that do form fade quickly, leaving little trace. Even the planet's faint rings and moons add to the sense of restraint. Everything about Uranus seems to prefer quiet understatement. It's almost as if, after the chaos of its creation, the planet simply decided to rest. This contrast is perhaps what makes Uranus so compelling. Where Jupiter shouts, Uranus whispers. Where Saturn dazzles with rings and storms, Uranus barely speaks above a hush. It's the introvert of the solar system, calm, reflective, and content to turn in silence. That calmness, though, has a beauty of its own. It offers a glimpse of equilibrium in a universe ruled by motion and heat. If you could drift through Uranus's upper atmosphere, it would feel almost meditative. The faint sunlight 70 times dimmer than on Earth would cast a gentle blue glow through the haze. The air would be still, the pressure low, and the world around you would hum softly with distant winds. Beneath, invisible layers of fluid hydrogen and ice would move in slow convection, their motions so gradual they might take years to complete a single cycle. There would be no lightning, no thunder, only the endless whisper of frozen gases shifting under gravity's hand. From far away, viewed through a telescope, this tranquility becomes mesmerizing. The light from Uranus is steady, unblinking, as if the planet itself refuses to flicker. While Jupiter's brightness pulses with storms and Saturn's rings flash like mirrors, Uranus remains constant, glowing faintly but persistently in the night sky. It's the still point at the edge of sunlight, the reminder that not all beauty requires motion. Scientists sometimes speak of Uranus as a planet in perfect thermal balance, but there's also a philosophical elegance to that description. Here is a world that no longer radiates heat, that has found equilibrium between energy in and energy out. It neither burns with fury nor freezes beyond endurance. It simply exists, serene and steady, in a cosmic quiet that few worlds achieve. In that sense, Uranus is almost like a lesson written in methane and light, a demonstration of stillness as a form of strength. It doesn't roar like Jupiter, it doesn't dance like Neptune, and it doesn't glitter like Saturn. It endures. It rolls through the dark without fuss or fanfare, glowing softly in its muted blue calm. If the solar system could meditate, this would be its chosen spot, a world where time slows, storms rest, and energy finds peace. The planet's quiet is not emptiness, it's harmony. Its calm face is the result of forces in balance, not absence of force. The silence is full, filled with the steady hum of physics in perfect symmetry. Uranus reminds us that stillness can be as dramatic as motion. Its calm is not boring. It's profound. It's the hush between cosmic symphonies, the pause that gives meaning to the music of the planets, and somewhere beneath its serene blue clouds the planet continues to spin sideways through eternity, perfectly at peace, the calmest world beneath the sun. For most of human history, Uranus was imagined as a quiet, bare world, a pale turquoise globe rolling through the darkness with no adornment, no ornaments, and no surprises. It seemed almost minimalist compared to its flamboyant neighbour Saturn, whose shimmering rings had captivated astronomers since Galileo first glimpsed them through his crude telescope in the early 1600s. But then, in 1977, Uranus revealed that it too carried its own faint jewellery. Rings so subtle that they could have gone unnoticed forever, whispering quietly around the planet in near silence. The discovery happened almost by accident. Astronomers in South America and Australia were preparing to observe what's known as a stellar occultation, a rare event when Uranus would pass directly in front of a distant star. As the planet drifted across the star's path, the light was expected to dim once, then brighten again, just as an eclipse might. The goal was simple: to measure the diameter of Uranus with greater precision. But when the data came in, something unexpected appeared. The starlight didn't dim just once. It flickered several times before and after the planet itself crossed. Each tiny dip in brightness lasted only a few seconds, yet the pattern was unmistakable. Something narrow, opaque, and orbiting Uranus was blocking the light. Within hours, astronomers realized they had stumbled upon a new discovery. The planet had a ring system. It was a quiet revolution in planetary science. For decades, Saturn had been the only known planet with rings, but Uranus's newly discovered system changed that view. It reminded scientists that the solar system's beauty often hides in subtleties, in details too faint for casual eyes to see. The rings of Uranus were not bright or broad. They were dark, narrow, and remarkably thin, like threads of shadow circling a muted world. Today, we know Uranus has 13 distinct rings, ranging from the bright, narrow epsilon ring to faint, dusty sheets that blend into the surrounding space. Unlike Saturn's icy brilliance, these rings are composed mostly of dark material, probably water ice coated with carbon-rich dust, radiation baked into near blackness. They reflect very little sunlight, which is why they escape detection for so long. Even through powerful telescopes, they are nearly invisible, detectable only by the faintest glints of light or by the way they obscure stars behind them. Each ring is astonishingly narrow. Some are only a few kilometers wide, thinner proportionally than a single hair across a human head. Yet despite their slenderness, their edges are sharply defined. This precision hints at something keeping them in line. Small moons called shepherd moons that orbit near the rings and act as gravitational caretakers. As these moons circle Uranus, their gravity gently nudges stray particles back into place, keeping the rings confined. Without these shepherds, the rings would quickly spread out and fade into a diffuse haze. Voyager 2's flyby in 1986 gave humanity its first direct view of these faint structures. As the spacecraft approached, it captured haunting images of thin, concentric arcs suspended in the dim blue glow. Unlike Saturn's bright and continuous bands, Uranus's rings appeared sparse, more like scratches of charcoal drawn against the void. They weren't symmetrical either. Some were brighter on one side, suggesting uneven particle distributions, possibly caused by the shepherd moons or subtle resonances within the system. The images were unlike anything astronomers had seen before, rings that didn't dazzle but whispered, quietly elegant in their restraint. One of the most striking features of Uranus's rings is how they nearly vanish when seen edge-on. Because the planet's axis lies almost flat, its rings are tilted nearly 98 degrees relative to the Sun, just like the planet itself. As Uranus orbits, there are moments, about once every 42 years, when the rings are perfectly edge-on from Earth's perspective. In those moments, they become all but invisible, as though they've dissolved into nothingness. Only faint shadows projected onto Uranus's upper atmosphere betray their presence. When sunlight returns to strike them more directly, they shimmer back into view, a delicate reappearance after decades of near invisibility. The ring's darkness tells a story of age and endurance. Fresh ice reflects light brightly, but these particles have been darkened over eons by cosmic radiation and micrometeorite impacts. Each grain of dust has been baked and battered, its surface chemically altered until it no longer gleams. The result is a set of rings that absorb most of the light that touches them, subtle, subdued, and quietly ancient. Scientists think these rings are relatively young in cosmic terms, perhaps no more than a few 100 million years old. They might have formed from the remnants of shattered moons, torn apart by Uranus's gravity when they drifted too close. The fragments from such an event would have spread into narrow belts, gradually ground down into smaller and smaller pieces. The shepherd moons that remain today could be the survivors of that destruction, the last remnants of what were once larger bodies. In the darkness of the outer solar system, the rings are more than ornaments. They're laboratories of motion. Each one represents a delicate balance of forces, particles colliding, sticking, drifting, and being shepherded back into alignment. The system functions like a cosmic clock, each orbit tuned to the next. Studying these interactions has given scientists insight into how planetary disks behave, from the early days of the solar system to the formation of galaxies themselves. Despite their faintness, Uranus's rings are far from lifeless. They occasionally display dynamic changes, arcs brightening, clumps appearing and dissolving. These fluctuations may be caused by unseen moons or by impacts from micrometeorites that briefly stir the dust. Even in their quiet way, the rings respond to the environment around them, vibrating with the rhythms of distant sunlight and gravity. Seen up close, if one could somehow drift among them, the rings of Uranus would likely appear as vast, dim plains of dark ice fragments, everything from sand-sized grains to boulders meters across. They would not sparkle like Saturn's. They would be ghostly and subdued, reflecting the faint sunlight in dull silver-grey glints. From within the rings, Uranus would hang in the sky as a massive turquoise disk, filling the heavens with its soft glow. The silence would be profound, broken only by the imagined whisper of particles colliding gently as they orbit. Because the planet's tilt is so extreme, its ring shadows stretch in eerie ways across its atmosphere. During equinoxes, when sunlight hits the system from the side, thin shadows sweep over the planet like the lines of an invisible sundial. These ephemeral patterns remind astronomers that the rings are not just ornaments but active participants in the planet's geometry. Silent companions that trace time on a world where seasons last for decades. Modern observations from the Hubble Space Telescope and ground-based observatories have even revealed faint outer rings far beyond those first detected in 1977. Some are diffuse and dusty, almost impossible to see except in scattered light. Two of them are unusually blue, possibly rich in fine ice grains that have somehow escaped darkening. They hint that the system is more complex than the early data suggested. a layered, evolving structure that still holds surprises. Despite all we've learned, there's something deeply human about the allure of Uranus's rings. They're understated, fragile, and easily missed, the opposite of grandstanding. While Saturn's rings demand attention, Uranus's must be sought out carefully, their beauty revealed only through patience. In that way, they reflect the character of the planet itself, modest, unassuming, yet quietly profound. They also remind us that not all wonders in the universe announce themselves with brightness or noise. Some shimmer at the threshold of invisibility, content to exist unseen. The rings of Uranus hum with that kind of quiet dignity. They orbit a sideways planet aligned to its peculiar tilt, keeping company with faint moons and the deep, cold silence of space. If Saturn's rings are an orchestra, Uranus's are a single flute note carried on the wind, subtle, fleeting, but beautiful in its restraint. If the planet Uranus seems quiet and reserved, its family of moons adds a whisper of drama and personality to that stillness. 27 are known so far, each moving in a graceful dance around their sideways world. Together they form a miniature tilted system, companions that orbit not in the usual upright way, but in line with Uranus's 98-degree lean. It's a strange, poetic sight to imagine, a planet rolling along its orbit like a wheel, and all its moons following suit, circling in that same sideways plane. Unlike the mythological naming traditions of most planetary systems, the moons of Uranus draw their identities from literature. Nearly all are named after characters from the works of William Shakespeare, and, in a few cases, from the poetry of Alexander Pope. It was a choice first suggested by John Herschel, the son of William Herschel, who discovered Uranus itself. Perhaps he thought the names of kings and fairies, lovers and dreamers, suited this strange and distant world better than another round of gods and goddesses. It's fitting. Uranus, the sky god, surrounded not by Olympians, but by actors in an eternal play. The 5 largest moons, Titania, Oberon, Ariel, Umbriel and Miranda, are the principal players on this stage. Each is distinct, with its own geography, colour and story. The rest are smaller, irregular bodies, many of them discovered only recently as telescope technology improved. But those 5 main moons, first seen through telescopes in the late 17 and 1800s, remain the heart of Uranus's system. Titania, the largest, is named for the queen of the fairies in A Midsummer Night's Dream. It spans about 1,500 kilometres across, roughly half the size of Earth's moon. Its surface is marked by enormous canyons and fault lines, the scars of ancient expansion as the moon's interior froze and cracked. Titania is brighter than its siblings, its icy crust reflecting the dim sunlight that reaches Uranus. Voyager 2 revealed vast valleys stretching for hundreds of kilometres, evidence that Titania once had internal activity, perhaps even a liquid ocean that has long since frozen solid. Oberon, Titania's counterpart and king of the fairies, lies slightly farther out. It is darker, older and more heavily cratered, a world of ancient impact scars and long shadows. Its craters gleam faintly with what appears to be fresh ice, thrown up from beneath the surface by collisions. Some of its walls are hundreds of meters high, towering over silent plains of frost. Oberon feels timeless, a place that has changed little for billions of years, orbiting at the edge of its tilted kingdom. Closer into Uranus are Ariel and Umbriel, 2 smaller moons with opposite personalities. Ariel is bright and young-looking, its surface crisscrossed by deep canyons and long ridges that suggest a history of tectonic stretching. There are signs that it may once have been geologically active, with ice flows and possible cryovolcanic eruptions. Eruptions not of molten rock, but of slushy mixtures of water and ammonia. Voyager 2's cameras caught glimpses of these features in 1986, showing a moon that had once tried to reshape itself before falling back into silence. Umbriel, by contrast, is the loner, dark, ancient, and heavily cratered. Its surface is coated with dark material, possibly carbon compounds that have accumulated over eons. It reflects very little sunlight, making it one of the dimmest large moons in the solar system. The most striking feature on Umbriel is a mysterious bright ring around a crater near its north pole, a spot nicknamed the Cheerio. Scientists still aren't sure why it stands out so vividly, but it gives Umbriel an oddly haunted appearance, like a shadowed moon wearing a single pale mask. And then there's Miranda, perhaps the strangest of them all. Small, irregular and battered, it looks as though it's been torn apart and reassembled. Its surface is a jigsaw of terrains that don't match, stitched together by cliffs and ridges so steep they defy reason. The most dramatic of these, known as Verona Rupes, is a cliff that plunges 20 kilometers, the tallest known in the solar system. If you were to fall from its edge, it would take more than 10 minutes to reach the bottom, drifting down through thin gravity and the icy air. Miranda's mismatched surface suggests a violent history. It may have shattered from an ancient collision and reformed under its own gravity, or perhaps internal heating once melted parts of it, allowing the crust to move and refreeze into chaos. Whatever happened, Miranda is a mosaic of frozen memory, the broken heart of Uranus's moon family. These 5 major moons are only part of a much larger ensemble. Beyond them, smaller moons orbit at various distances, some so faint that they were first detected only in the 21st century. Closer to the planet lie inner moons like Cordelia and Ophelia, which act as shepherds for Uranus's narrow rings, keeping the icy debris in line with their gravitational pull. Others, like Puck, Portia, Rosalind and Belinda, fill the gaps between the main ring system and the outer moons. Their names, drawn from Shakespeare's plays and Pope's poems, give the Uranian system a peculiar charm, part science, part theatre. Farther out, beyond the orbits of the major moons, lies a cluster of small, irregular satellites with elongated, tilted paths. These are likely captured objects, fragments of the early solar system that were snared by Uranus's gravity long after the planet formed. They move in eccentric orbits, some even retrograde, circling the planet in the opposite direction of its rotation. These distant wanderers complete the Uranian moon family, adding complexity to a system that is already tilted, layered, and quietly eccentric. Because Uranus itself is tipped over, all its moons share in that same peculiar geometry. Their orbits lie along the planet's equatorial plane, which means they circle not around the planet's middle as we picture it, but around its sides. From above the solar system, they appear to be rolling with Uranus like marbles in a sideways groove. As the planet turns, the moons follow, moving in and out of decades-long light and darkness. For half of Uranus's 84-year orbit, one pole of the planet, and its attendant moons, faces the sun continuously, basking in weak daylight. For the other half, they are cast into deep shadow. Each moon therefore experiences seasons that last for decades, just as the planet does. This alignment creates stunning cosmic choreography. When Uranus approaches its equinoxes, the sun shines along the equatorial plane, illuminating all the moons in a flat, glowing disk. Their shadows sweep across the planet's atmosphere in parallel lines, tracing arcs that fade into the distance. Occasionally the moons even pass directly in front of one another, or cast eclipses across Uranus's cloud tops. These rare alignments occur only twice every 84 years, moments when the tilted system briefly reveals its perfect symmetry before returning to its sideways solitude. The composition of Uranus's moons offers clues about their origins. The larger ones are mixtures of roughly equal parts rock and water ice, suggesting they formed from the same disk of material that once surrounded the young planet. Their densities are low, their surfaces ancient, and their features carved by both impacts and internal shifts. The smaller moons, especially those orbiting far out, are darker and likely captured objects, fragments of asteroids or comets drawn in by gravity. This mix of native and adopted worlds gives Uranus a moon system as complex as it is beautiful. Voyager 2's flyby provided humanity's only close look at these distant companions, and the images it sent back still captivate scientists. From the bright valleys of Ariel to the shadowed plains of Umbriel, from the icy fractures of Titania to the broken mosaics of Miranda, the moons of Uranus display a diversity that defies their quiet appearance. Each one tells a fragment of the planet's history, stories of collisions, freezing, and long, slow transformation. In the decades since Voyager's visit, telescopes on Earth and in orbit have refined our understanding of these worlds. We now know that some of the moons may still harbour subsurface oceans, kept liquid by traces of heat and the pull of Uranus's gravity. If true, those hidden seas would make them potential havens for chemical complexity, perhaps even precursors to life, though in a place so remote and cold, that idea feels more poetic than probable. Still, the possibility adds another layer of intrigue to this already extraordinary family. Viewed together, the moons of Uranus are a portrait of quiet endurance. They have orbited their planet for billions of years, following its sideways path through the dark, rolling in unison around their tilted sun. Each is unique, yet all share in the same geometry of imbalance, the same rhythm of light and shadow. They move not with the precision of a clock, but with the grace of a slow, endless dance, companions in a world that itself spins against the grain. Of all the moons that circle Uranus, none are as haunting or as puzzling as Miranda. It's small, only about 500 kilometers wide, barely large enough to be called a world at all, yet its surface looks like the result of some cosmic accident. When Voyager 2 flew past in 1986, the spacecraft sent back images that stunned scientists. Instead of a smooth, cratered moon, they saw something that looked broken, rearranged and stitched together. Vast cliffs towered above plains of ice. Ridges and grooves crossed each other at impossible angles. It was as if Miranda had been shattered into pieces and then reassembled by an artist who couldn't remember exactly where each part belonged. The first thing that strikes anyone looking at Miranda is the sheer mismatch of its terrain. Different regions don't blend together gradually. They collide, overlapping like tectonic plates that never quite fit. Some areas are ancient and heavily cratered, suggesting billions of years of impacts. Others look strangely young, with smooth ice and long parallel grooves that hint at recent geological activity. It's a world of contradictions, where frozen plains meet jagged ridges and nothing seems entirely settled. Among Miranda's most dramatic features are its canyons, vast scars that slice through its icy crust. The most famous of these, Verona Rupes, is a cliff so tall it defies imagination. At 20 kilometers high, It's roughly 10 times the depth of the Grand Canyon. If you were somehow standing at the top and stepped off, it would take over 10 minutes to reach the bottom, even in Miranda's weak gravity. The fall would be silent through a pale blue sky, faintly lit by distant sunlight, onto a surface frozen harder than stone. Verona Rupes is not an isolated formation. It's part of a network of cliffs, faults, and fractures that crisscross the moon, evidence of a violent and restless past. What could have created such chaos on a moon so small? Normally, objects of Miranda's size are geologically dead, too small to retain internal heat, too cold for tectonic movement. Yet Miranda's landscape tells a different story. It shows signs of resurfacing, as though parts of its crust once melted, flowed, and froze again. Some scientists believe Miranda may have experienced periods of internal heating driven by tidal forces. As the moon orbited Uranus, gravitational interactions with larger moons like Ariel and Umbriel could have stretched and squeezed it, generating enough friction to melt the ice beneath its surface. When the heat dissipated, the crust would have refrozen, leaving behind ridges and valleys where the ice had shifted. Another, even more dramatic theory suggests that Miranda was once completely destroyed, torn apart by a massive impact or by tidal forces when it strayed too close to Uranus. Afterward, gravity may have slowly pulled the fragments back together, reassembling the moon into its current patchwork form. This idea could explain the mismatched nature of its terrain. Pieces of the original crust falling back in random orientations, creating a surface of overlapping regions and uneven layers. If true, Miranda would be a moon literally rebuilt from memory and mistake, a world that forgot what it once was and quietly put itself back together again. Voyager 2's flyby provided only a brief glimpse, but that glimpse changed how scientists viewed icy moons forever. Before that encounter, few expected such small bodies to show complex geology. Miranda proved that even tiny worlds could harbour dynamic histories. The images revealed regions called coronae, enormous oval-shaped structures surrounded by ridges and troughs. Each corona spans hundreds of kilometres and seems to mark an area where the surface rose and fell repeatedly. The most prominent of these, Arden Corona, looks like an enormous patch sewn into the crust, bordered by looping faults that might once have marked the edge of an uplifted dome. Another, Elsinore Corona, has concentric rings that resemble ripples frozen in time. These coronae are unlike anything found elsewhere in the solar system. They may have formed as warm material from within, Miranda pushed upward, cracking and deforming the brittle crust. When the heat faded, the domes collapsed, leaving behind the strange circular scars we see today. In some regions, the ridges form patterns so complex that scientists jokingly compared them to patchwork quilts. It's an apt description. Miranda really does look stitched together from mismatched pieces. The variety of textures across its surface also suggest that Miranda's crust has been recycled multiple times. Older, darker terrains coexist with younger, brighter ice that may have resurfaced comparatively recently. Craters, while present, are not as densely packed as on other moons, implying that some regions has been refreshed within the last billion years. Still ancient by human standards, but geologically young for a world so distant. From a distance, Miranda might seem serene, but up close it's a landscape of sharp contrasts and endless drama. The cliffs and ridges catch the dim sunlight at sharp angles, casting long shadows across the plains. In the faint blue glow reflected from Uranus, the ice gleams like glass. The gravity is so weak that an object dropped from a height would drift gently downward rather than plummet. It's a place that feels frozen in motion, as though time slowed down and every fracture, every ridge was captured mid-gesture. What makes Miranda particularly intriguing is how much mystery remains. Voyager 2 only imaged one hemisphere of the moon. The other side has never been seen in detail. For all we know, it could be entirely different. Smoother, rougher, or hiding features even more bizarre. Until another spacecraft returns to Uranus, we can only speculate about what lies beyond that unobserved horizon. It's humbling to think that half of this world remains invisible, its secret still sleeping in the dark. Miranda's orbit also adds to its character. It lies close to Uranus, just over 130,000 kilometers above the cloud tops, roughly 1/3 the distance between Earth and the Moon. From its surface, Uranus would dominate the sky, an enormous turquoise disk filling the heavens, casting a ghostly light across the landscape. Because Uranus is tilted, Miranda's own sunlight and shadow cycles would be extreme. For decades at a time, one hemisphere would face continuous day while the other languished in twilight, until the planet's slow rotation gradually reversed the roles. Despite its fractured appearance, Miranda's orbit is remarkably stable. It moves in near-perfect synchrony with the rest of Uranus's inner moons, maintaining the same sideways inclination as its parent planet. Together they form a balanced but precarious system, where gravitational tugs between moons subtly shape their orbits, and perhaps once fueled the internal heating that gave Miranda its scars. In many ways, Miranda feels like a reminder that even broken things can be beautiful. Its surface tells a story of destruction and renewal, of energy locked inside ice and released in bursts that reshaped an entire world. It's a testament to the resilience of matter, how gravity, that quiet sculptor, can take chaos and turn it into order again. If we could stand on Miranda's icy plains, the silence would be absolute. The only movement would be the slow arc of Uranus's rings overhead and the faint glow of sunlight filtering through the haze. The cliffs would loom like frozen waves, and the valleys would stretch into the dim horizon, each one carved by forces that have long since gone still. In that silence, you could almost feel the moon's history, its shattering, its rebuilding, and its long, patient wait beneath the cold light of a distant sun. Miranda is more than just a moon. It's a monument to imperfection, a fractured jewel that reminds us that even in the coldest corners of the solar system, creation is rarely tidy. Worlds can break, rebuild, and endure. And perhaps that is Miranda's quiet message, carried in its mismatched terrain and colossal scars, that beauty can emerge from mistakes, and that memory, even when fragmented, can still find its shape again. Seen through a telescope, Uranus glows with one of the most soothing colours in the solar system, a gentle turquoise, like seawater in the shallows of a quiet lagoon. It's neither the vivid blue of Neptune nor the golden warmth of Saturn, but something between, calm, muted, and strangely serene. It's easy to imagine the planet as peaceful simply because of its colour, as though its very light carries the hush of distance. But that tranquil hue isn't an accident of perception. It's a story of sunlight, chemistry, and the way the universe plays with colour. The secret behind Uranus's soft glow lies in its atmosphere. The air there is made mostly of hydrogen and helium, but it also contains a trace gas, methane, that makes all the difference. Methane has a curious relationship with light. When sunlight reaches Uranus, it encounters methane molecules in the upper layers of the atmosphere. These molecules absorb the red and orange wavelengths of sunlight, while letting blue and green light pass through and scatter. The result is that all the warmer tones are stripped away, leaving behind that cool turquoise hue. It's the same principle that makes Earth's sky blue, but on Uranus the effect is far stronger. Our own atmosphere scatters sunlight in every direction through nitrogen and oxygen molecules, but methane is more selective, taking a particular bite out of the red end of the spectrum. The sunlight that escapes back into space from Uranus is filtered, softened, and recolored by its long journey through that methane haze. What we see from afar is the leftover light, the quiet remainder of the sun's spectrum after the reds and golds have been swallowed up. At first glance, Uranus and Neptune look similar, both ice giants, both wrapped in blue, but look closer and you'll see a difference. Neptune is a deeper, richer blue, almost sapphire, while Uranus is paler and greener, like a piece of frosted glass. This subtle contrast puzzled astronomers for years. If both planets have methane-rich atmospheres, why should their colours differ at all? The answer seems to lie in the details, the thickness of their hazes, the amount of sunlight they reflect, and perhaps the chemistry that takes place high above their clouds. Recent studies suggest that Uranus's atmosphere contains more high-altitude haze than Neptune's, a thin veil of fine particles that brightens the planet and mutes its colour. These particles likely form when ultraviolet light from the sun breaks down methane, producing heavier hydrocarbons like ethane and acetylene. Over time, these molecules clump into aerosols that float in the upper atmosphere, scattering light in a softer, more diffused way. The result is that Uranus's blue becomes pastel, lighter, quieter, more subdued, while Neptune's clearer skies allow the deeper blues to shine through. It's an exquisite example of how delicate physics can define beauty on a planetary scale. A fraction of a % difference in composition, a slightly thicker layer of haze, and a world's entire character changes. If Uranus were just a little clearer, it might glow as darkly as Neptune. If its haze were denser, it might fade toward grey. Instead, it sits perfectly between, a planet coloured by balance. The sunlight that reaches Uranus has travelled nearly 3 billion kilometres to get there. By the time it arrives, it's already faint, less than 1% as strong as the light that warms Earth. What's left filters through layers of methane, scattering off tiny particles of ice and haze before returning to space. The light we see from Uranus, then, is not raw sunlight, but the memory of sunlight, light that has been quieted, softened, and reshaped by its long journey. That may be why the planet's colour feels so gentle to the eye. It is light that has learned patience. That subtle filtering doesn't just affect the colour we see, it shapes the way Uranus looks across different wavelengths. In infrared light, the planet reveals deeper structure, faint bands, temperature variations, and cloud systems hidden beneath its outer layers. But in visible light, those features disappear, veiled by the scattering effect of methane and haze. The result is the familiar smooth disk, uniform and calming. The chemistry of colour here is also the chemistry of concealment. If you could descend into the atmosphere of Uranus, the colours around you would shift as you went deeper. Near the top, sunlight would scatter into soft turquoise and green. As you fell through thicker clouds, the haze would dim and the light would fade toward indigo. The deeper you went, the darker it would become, until eventually all colour vanished and you entered a realm of pure shadow and pressure. The planet's visible calm would give way to hidden turmoil, storms, convection, and the restless physics of a fluid interior. But from the outside, none of that shows. Seen from Earth, Uranus keeps its composure. This quiet colour is more than aesthetic, it's a clue to the planet's history. The abundance of methane and the faintness of hydrogen and helium tell scientists how Uranus formed. In the cold outer regions of the early solar system where sunlight was weak, volatile compounds like water, ammonia and methane condensed into ices. These materials became the building blocks of Uranus and Neptune. Their colour, then, is not just a trick of light. It's the visible echo of their birthplaces, a reminder of the frozen chemistry that built them. To the human eye, that soft turquoise hue seems almost restful, but to astronomers, it's a spectrum rich with information. By measuring exactly how much red light is absorbed, scientists can estimate the methane concentration. By studying the faint variations in colour across the disk, they can infer the presence of clouds, winds, and even subtle temperature gradients. Every shade of blue tells a story of sunlight filtered through gases, of atmospheric dynamics, of time and distance. When Voyager 2 first photographed Uranus, the planet's delicate colour was one of its defining surprises. Against the black of space, it glowed like a luminous marble. Featureless but elegant. The camera's sensors, designed for science, ended up capturing something artistic instead. The simplest colour palette imaginable, just blue and black, yet filled with quiet emotion. Decades later, telescopes continue to refine our view, revealing hints of green and cyan that shift with the planet's seasons. Uranus's appearance is not static but alive, changing slowly as sunlight plays across its tilted poles. There's also something deeply symbolic about the colour of Uranus. Blue, in human culture, is often associated with tranquility, distance, and reflection, the colour of deep water and open sky. On Uranus, those associations feel literal. It is a world defined by distance, wrapped in calm, and illuminated by filtered light. Its colour tells us that even in the vastness of space, beauty can emerge from simplicity, from one molecule quietly deciding which wavelengths to keep and which to let go. When you look at Uranus through a telescope, the light reaching your eye left the Sun hours ago, travelled billions of kilometres, and passed through an atmosphere shaped by chemistry older than life on Earth. Every photon you see has been filtered, softened, and scattered into that turquoise tone. You are seeing sunlight that has been reborn in the language of methane. The universe is full of violent colours, the red glare of stars, the golden storms of Jupiter, the fiery orange of Mars. Uranus stands apart, content to glow in peace. Its colour doesn't demand attention, it invites stillness. It is the visual expression of serenity itself, a planet coloured by the quietest light. In January of 1986, humanity came closer to Uranus than ever before, and for a brief moment we saw the sideways world up close. The visitor was Voyager 2, the second of a pair of spacecraft launched in the late 1970s to explore the outer solar system. By the time it reached Uranus, Voyager had already flown past Jupiter and Saturn, each encounter rewriting what we knew about the planets. Now, after nearly a decade of travel, it was about to make history again. The first and only spacecraft to ever visit Uranus. The encounter was fleeting. Voyager 2 didn't stop or orbit. It simply swept past at nearly 80,000 kilometers per hour, gliding just 81,000 kilometers above the planet's cloud tops. The entire flyby lasted only a few hours, but in that time it gathered an extraordinary wealth of information, data that scientists would spend years unravelling. As the spacecraft approached, its cameras began capturing images of the pale blue disk growing larger with each passing hour. To the human eye, those first pictures seemed almost disappointing. After the chaos of Jupiter's storms and the golden complexity of Saturn's rings, Uranus looked eerily plain, a featureless sphere, softly glowing, almost too smooth to be real. Scientists had expected more texture, more contrast, more weather. Instead, they found a world so calm it seemed asleep. The stillness was unsettling, a quiet so profound it bordered on mysterious. But while the visible surface offered little drama, Voyager's instruments told a richer story. Beneath that serenity, Uranus was full of surprises. The spacecraft's magnetometer detected a magnetic field so wildly off-center that it seemed to twist and wobble through space, misaligned with the planet's rotation by nearly 60 degrees. The readings defied all expectations and confirmed that Uranus's magnetic heart was every bit as peculiar as its tilt. Other instruments measured the planet's temperature and composition. They confirmed that Uranus's atmosphere was made mostly of hydrogen and helium, with traces of methane giving it its trademark turquoise hue. The temperatures were shockingly cold, around -224 degrees Celsius, colder even than Neptune despite being closer to the Sun. That discovery deepened the mystery of Uranus's missing heat, suggesting an internal structure unlike any other planet's. Voyager's infrared sensors found that Uranus emitted almost no excess energy at all, implying that its interior had long since gone quiet. There were no signs of the deep convection that drove Jupiter's and Saturn's clouds into motion. Instead, Uranus's atmosphere was still, its winds weak, its energy spent. The planet seemed at peace, a frozen relic of cosmic history drifting through the dark. Voyager's cameras also turned toward the rings, capturing them for the first time in detail. Unlike Saturn's broad and brilliant bands, Uranus's rings appeared narrow and dark, composed of material that reflected almost no light. They were not the radiant ornaments of a showy world, but delicate, whisper-thin structures circling in near silence. The spacecraft revealed 13 distinct rings, each confined by small shepherd moons, whose gravity kept the icy debris from spreading. Against the faint blue glow of Uranus, the rings looked like charcoal lines drawn on glass. As Voyager swept through the planet's magnetic environment, it also measured the flow of charged particles, electrons and ions trapped by Uranus's magnetosphere. What it found was unlike anything seen before. The magnetic field flipped orientation every time the planet rotated, creating a twisted, corkscrew-shaped tail of energy, stretching millions of kilometers behind it. For the mission's engineers, it was a technical challenge. For scientists, it was a revelation. Even the invisible forces around Uranus leaned sideways. Perhaps the greatest treasures of the encounter, however, were the images of Uranus's moons. Before Voyager, only a handful of them had been observed clearly from Earth. The flyby transformed them from points of light into worlds. Each moon revealed a personality as distinct as any planet's. Titania appeared fractured and scarred, with canyons running hundreds of kilometers long. Oberon, farther out, showed dark plains and bright crater rims that hinted at ice beneath its surface. Ariel, bright and youthful, displayed valleys and ridges that suggested geologic activity, a moon that had once been alive with movement. Umbriel, by contrast, was ancient and dark, its landscape marked by craters that gleamed faintly with icy frost. And Miranda, the smallest of the major moons, stole the show entirely. Its surface, a chaotic collage of ridges and cliffs, looked almost too strange to be natural. Scientists stared in disbelief at Verona Rupes, the enormous cliff plunging 20 kilometers down, and at the patchwork regions that seemed stitched together by cosmic hands. In one swift flyby, Voyager had turned Miranda from a dot into a mystery. For planetary scientists, this was both exhilarating and bittersweet. Voyager 2 could only glance at Uranus as it passed. There would be no orbit, no return, and no second look. The spacecraft was already moving too fast to stop. After just a few days of intense observation, it began its long journey outward toward Neptune, leaving Uranus to fade once more into the dark. In total, humanity's visit lasted less than a week, a momentary hello after billions of years of silence. The data Voyager gathered was so rich that it took years to fully analyze. Each file, transmitted slowly back to Earth across the vast gulf of space, represented a tiny piece of a larger puzzle. From those fragments, scientists reconstructed the world we know today. The tilted axis, the faint rings, the 27 moons, and the strange magnetic field. Before Voyager, Uranus was little more than a name and a colour. After Voyager, it became a world, serene, sideways, and deeply enigmatic. The mission also changed how we think about exploration itself. The success of Voyager's encounter with Uranus proved that even brief flybys could transform understanding. A few hours of observation had rewritten the textbooks. It showed that the most distant worlds could be reached with persistence, precision, and a bit of boldness. In 1986, Uranus became the farthest planet ever visited by a spacecraft, a record it held until Voyager 2 continued on to Neptune 3 years later. There's something poetic about that fleeting visit. The planet that spends decades in daylight and decades in darkness, rolling slowly through the void, was met by a traveller that stayed for only a moment. Yet that moment was enough. In that short encounter, humanity glimpsed one of the quietest corners of the solar system and left its mark there, however faintly. Voyager's images, when viewed today, still evoke the calm of that distant world. The planet's surface glows softly, its rings encircle it like threads of shadow, and its moons hang in perfect stillness. The photographs are grainy by modern standards, but they carry a kind of honesty, the humbling beauty of discovery at the limits of what was then possible. After the encounter, Voyager 2 continued outward. Its cameras turned off to conserve power. It left Uranus behind forever, drifting into the deep where the sun's light grows weaker than starlight. Yet, in a sense, part of it remained there. A trace of human curiosity, a whisper from a civilization that had looked across 3 billion kilometers of emptiness just to see what was there. Since that flyby, no spacecraft has returned to Uranus. All that we know of the planet up close comes from those few days in 1986. The data, still studied decades later, continues to reveal new details, slight variations in the rings, refinements to the moon's orbits, hints of atmospheric patterns once overlooked. It's remarkable to think that a single brief visit could sustain scientific discovery for generations. For now, Uranus remains as Voyager left it, cold, calm and distant, turning sideways beneath the dim light of the sun. The spacecraft's path carried it onward to Neptune and beyond, into the endless dark between the stars. But somewhere in that vastness, one could almost imagine a quiet echo, a trace of that passing moment when Earth reached out across billions of kilometers to greet a planet that rolls through eternity. After Voyager 2's departure in 1986, Uranus faded once more into silence. For a world that rolls through eternity on its side, time moves differently. Slow, deliberate, almost unbothered. But for humanity, 3.5 decades have now passed without a single spacecraft returning to that pale turquoise planet. No close-up images, no new readings, no whispers from the edge of the sun's warmth. Of all the major planets in the solar system, Uranus has remained the most forgotten. In those years, attention turned elsewhere. Voyager 2 continued on to Neptune, stealing the headlines with its vivid pictures of the Great Dark Spot. Then came Galileo to Jupiter, Cassini to Saturn, Juno, New Horizons, each mission illuminating another corner of the outer solar system. Meanwhile, Uranus simply kept spinning, serene and sideways, waiting for someone to remember it. The last close images we have are still the ones Voyager sent back during its brief encounter. Pictures stored in archives, occasionally reprocessed with modern software but still the same frozen moments from 1986. It's not that scientists forgot Uranus deliberately. It's just that visiting it again has always been hard. The planet is far away, nearly 3 billion kilometers from the Sun, and getting there requires a rare alignment of orbits and an enormous amount of fuel. Missions to Jupiter or Saturn can rely on powerful sunlight and convenient gravity assists. A mission to Uranus would be a slower, colder journey, lasting more than a decade and demanding great patience from everyone involved. For many years that patience seemed too much to ask. And yet, in recent times, something has begun to change. The forgotten planet has started to capture attention again, not through new images, but through the quiet persistence of curiosity. Astronomers, planetary scientists and engineers have begun to argue that Uranus might, in fact, be the most intriguing world left unexplored. It's not just that we know so little about it, it's that what we do know makes it uniquely strange. For one thing, Uranus and Neptune represent an entire category of planets, the ice giants, that dominate our galaxy but remain poorly understood. When astronomers look at distant star systems, the most common type of planet they find are roughly the size of Uranus and Neptune. These mini-Neptunes, as they're often called, seem to outnumber Earth-like and Jupiter-like planets combined. Yet we have only 2 examples nearby, and we've studied them up close for only a few days each. If we want to understand the most common kind of world in the universe, Uranus may be the perfect place to start. That's why, in the 20s, proposals began circulating for a new mission, one that would not just fly by, but stay. The idea of a Uranus orbiter and probe has gathered remarkable momentum, championed by scientists who see the planet as the next great frontier of planetary exploration. The mission's goal would be simple yet profound: to finally spend time with Uranus, to orbit it for years rather than hours, and to send a small atmospheric probe diving into its clouds to taste what Voyager could only glimpse. Such a mission could answer questions that have lingered for nearly 40 years. Why is Uranus so cold, emitting almost no internal heat compared to its twin Neptune? What is the structure of its interior, and does it really contain layers of exotic materials like superionic water, ice that conducts electricity? How does its off-center magnetic field form and behave? What processes drive its faint pastel atmosphere, and how do its seasons unfold across decades of sunlight and shadow? Each question is a doorway into deeper understanding, not just of Uranus, but of planets in general. A Uranus orbiter could also revolutionize our view of its moons. Voyager's images of Miranda, Titania, Oberon, Ariel, and Umbriel were tantalizing but incomplete. Half of each moon remains unseen in detail, hidden in shadow during the flyby. An orbiter could map those missing hemispheres, study the surface compositions, and even search for signs of subsurface oceans, pockets of liquid water that might exist beneath icy crusts, warmed by internal heat or tidal flexing. These moons, quietly circling their sideways world, could turn out to be as complex and dynamic as Jupiter's Europa or Saturn's Enceladus. Then there are the rings, dark, narrow, and mysterious. High-resolution cameras could watch how they shift over time, how they interact with the shepherd moons that keep them confined, and whether new, fainter rings wait farther out. Infrared and ultraviolet sensors could reveal their composition and age, perhaps even tracing their origins to shattered moons or leftover debris from Uranus's tumultuous past. The challenges of such a mission are enormous, but not impossible. Engineers envision using gravity assists, perhaps from Jupiter, to fling a spacecraft toward Uranus. The journey would take about 13 years, meaning that if the mission launched in the early 2030s, arrival would come around the mid-2040s. By then, Uranus will be approaching its next equinox, a period when both its hemispheres receive sunlight equally, the perfect time to observe how its long seasons transition. Timing, as always with Uranus, would be everything. A probe dropped into the atmosphere could provide the first direct measurements of temperature, wind, and composition. It would fall through layers of methane haze, reporting conditions until pressure and heat silenced it. In that short descent, it would gather more data about Uranus's atmosphere than all previous missions combined. Meanwhile, the orbiter above could watch storms form, map the magnetic field, and record the delicate interplay of light and shadow across the planet's rings and moons. The potential rewards of such a mission extend far beyond Uranus itself. Understanding its atmosphere and internal heat could reshape our knowledge of how planets retain or lose energy over time. Studying its magnetosphere could reveal new principles about magnetic field generation in worlds that lack molten metal cores. And exploring its moons could help answer one of the oldest questions in science. Where and under what conditions could life, even microbial, find a foothold beyond Earth? In 2022, the American National Academies of Sciences released its Decadal Survey, a once-a-decade report that sets priorities for planetary exploration. For the first time, Uranus topped the list. The recommendation was clear. The next major flagship mission should be a Uranus orbiter and probe. Scientists around the world celebrated quietly. After decades of neglect, Uranus had finally stepped into the spotlight again. If all goes well, the mission could launch in the early 2030s. It would spend more than a decade travelling outward, sleeping through the cold until it reached its destination. Then, in the 2040s, long after many of its planners have retired, it would awaken. It would approach the sideways world and settle into orbit, becoming the first artificial moon of Uranus, a silent companion studying a silent planet. For the first time in human history, we would see Uranus's hidden hemisphere, the side never illuminated during Voyager's visit. We would watch seasons shift in real time and perhaps witness the awakening of its calm atmosphere as sunlight slowly creeps across its tilted poles. The prospect feels almost poetic, to return after so long, to finally listen again to a planet that has waited patiently in the dark. The data Voyager sent back in 1986 was enough to fill libraries, yet it was only a taste, a whisper from a fleeting encounter. Now technology has caught up with our curiosity. high-resolution cameras, sensitive spectrometers, and magnetometers far beyond Voyager's capabilities could transform our understanding of the ice giants entirely. There's something fitting about Uranus becoming the next great destination for planetary exploration. For centuries, it has stood apart, quiet, distant, and oddly serene, a world defined by its difference. It doesn't draw attention like Jupiter's storms or Saturn's rings. It waits, understated but immense. Its time may finally be coming, not in sudden fanfare, but in the slow, deliberate rhythm that seems to define everything about it. When the Uranus orbiter and probe eventually departs Earth, it will be the continuation of a story that began in a candlelit observatory in 1781, when William Herschel first spotted the planet moving among the stars. It will also be a tribute to Voyager 2's brief but profound visit, a promise to return to the world we once saw only in passing. For now, Uranus continues to drift through the cold, tilted twilight, keeping its secrets close. But soon, perhaps within a single human lifetime, another spacecraft will arrive. It will glide into orbit, send its first signal home, and once again the forgotten planet will have a voice. Light behaves differently on Uranus. It arrives thin and tired, having crossed nearly 3 billion kilometers of space, stretched and softened by the journey. By the time it reaches the planet, sunlight is no longer golden or fierce. It's a whisper, a pale echo of what warms Earth. The Sun, seen from Uranus, is only a small disk in the sky, not much brighter than a pinhead of white fire, giving off just enough light to reveal outlines, shadows, and a delicate sense of direction. Here, illumination feels more like suggestion than certainty. And yet, in this faintness, beauty thrives. The light that filters through Uranus's atmosphere moves through layers of methane and haze, scattering into turquoise and sea green tones. It gives the planet its gentle colour and fills its skies with the softest light in the solar system. The air, so cold that even gases seem reluctant to move, bends sunlight into long ghostly gradients. On Uranus, there are no crisp boundaries between day and night, only shades of calm. Imagine standing on one of its icy moons. The sun would hang low, its glow reduced to a distant shimmer, casting shadows that stretch for kilometers. When Uranus's rings catch that light, they glint faintly like the edge of a blade, silver grey, almost imperceptible, but perfectly defined against the darkness. The moons themselves would glow with reflected turquoise, their surfaces faintly illuminated by light that has already been scattered twice, first by the planet's atmosphere and then by the rings. Even darkness here is touched by colour. Because Uranus is tilted on its side, its relationship with sunlight is among the strangest in the solar system. One pole spends 21 years in constant day, the other in endless night. As the planet rolls through its 84-year orbit, those rolls slowly reverse. Seasons unfold not as cycles of months but of generations. When the sun finally rises over a pole after decades of darkness, it does so with a slow, deliberate grace. The light creeps sideways across the horizon, casting immense shadows that crawl across the ice like the hands of a clock that moves once per century. At the equator, things are gentler but no less strange. The planet's tilt ensures that sunlight always slants in at awkward angles, so every sunrise and sunset last for hours. The light changes slowly, not golden and fiery, but cold and silver, as though time itself hesitates. Even at noon, the brightness never reaches full day. The sun hovers low, filtered through the methane haze, turning the world into an eternal twilight. This twilight gives Uranus an atmosphere of calm that's hard to describe. It isn't dark enough to feel ominous or bright enough to feel alive. It simply is. A quiet in-between state that mirrors the planet's subdued energy. The physics behind it is simple, but the effect is almost poetic. Methane molecules absorb red light, leaving only the cooler tones of blue and green. Scattering diffuses that light in every direction, softening it further until the planet's surface, rings and moons all seem to float within a single shared glow. It's the physics of serenity, the way light behaves when stripped of all intensity. On Earth, shadows are fleeting. They move with the sun, shrinking and stretching over the course of a day. On Uranus, shadows linger for decades. Entire landscapes could lie in twilight for half a human lifetime before seeing the light again. It's a rhythm of illumination so slow that no living creature, if there were any, could ever perceive change within its lifetime. Each sunrise would be a geological event, each sunset a legend. This strange dance of light and shadow also tells a scientific story. The way light scatters through Uranus's atmosphere reveals the density, composition, and temperature of its layers. By studying how the planet reflects and absorbs sunlight, scientists can infer what lies beneath the clouds, how thick the haze is, how deep the methane extends, how pressure and chemistry shape the world's colour. Light becomes not just a way to see, but a way to understand. Even from afar, telescopes capture this delicate play of brightness. When Uranus is near equinox, sunlight grazes its equator, and the rings cast thin, razor-like shadows across its cloud tops. These shadows shift slowly as the planet turns, tracing silent paths that tell astronomers where each ring lies. At solstice, the rings face the sun directly, gleaming faintly while the polar regions either bask in perpetual glow or lie hidden in darkness. Every phase, every tilt, every soft glint of reflected light becomes a clue, a quiet language written in colour and shadow. For centuries humans have equated light with knowledge. To see clearly is to understand. To bring something into the light is to make it known. On Uranus, that symbolism feels literal and fragile. The planet exists on the very edge of sunlight, where brightness fades into uncertainty. Every photon that reaches it is a survivor of the dark, a fragment of illumination that has crossed unimaginable distance to reveal just a hint of what lies beyond. The light on Uranus reminds us that discovery doesn't always come in brilliance. Sometimes it comes in whispers. Even in the most remote places, light persists. It bends, scatters, and reflects until it finds a way to be seen. On Uranus, it paints an entire world with tranquility, proof that illumination can exist without intensity, and beauty without boldness. The planet's turquoise glow is the cosmos rendered in pastel, a symbol of quiet endurance. If we think of Uranus as a metaphor, it's a world that teaches patience. It turns slowly, receives little sunlight, and spends decades in shadow. Yet it still shines. Its glow, faint but unmistakable, proves that even on the outskirts of light, something can reflect enough to be seen. In that sense, Uranus is more than a planet. It's a reminder of resilience, that knowledge, like sunlight, will always find a surface to touch. For astronomers, the planet's distant radiance is also a challenge. Every photon of light they collect from Uranus carries with it a story of survival. Light that has crossed space, bounced through an atmosphere of methane and ice, and journeyed home to the lens of a telescope. Through that faint signal they read the planet's temperature, chemistry, and storms. In every spectrum they see a balance between presence and absence, brightness and shadow. In a cosmic sense, Uranus represents a boundary. It is the last of the classical planets, the last world visible to the naked eye. Beyond it lie only the realms of ice and darkness, Neptune, the Kuiper belt, and the infinite quiet beyond. To look at Uranus is to stand at the threshold between what the sun still warms and what it barely touches. Its dim light is the universe's way of reminding us that illumination does not end abruptly. It fades gracefully, like twilight stretched to eternity. Perhaps that is why Uranus feels symbolic in a way few other planets do. It sits at the edge of sunlight, of attention, of understanding, yet it continues to glow, softly and persistently. In its muted colours and long shadows, it embodies the balance between knowing and not knowing, between clarity and mystery. It is a world defined by faintness, yet that faintness is its beauty. In the end, light on Uranus is more than illumination. It's philosophy. It's the meeting point of physics and wonder, of measurable reality and quiet awe. To study it is to explore not just how light behaves, but what it means to see. To perceive something far away, faint and fragile, yet still undeniably real. In the quiet reaches of the solar system, far beyond the warmth of the sun, two great spheres drift through the dark, Uranus and Neptune, the ice giants. They are often called twins, and at first glance it's easy to see why. Both are almost the same size, both glow with shades of blue, and both are composed of similar materials: hydrogen, helium, water, methane, and ammonia. Yet despite their shared heritage, they could hardly behave more differently. One is calm, subdued, and cold, a planet of stillness. The other is turbulent, bright, and full of motion, a restless ocean in the void. Two worlds born alike, one restless, one still. In many ways, Uranus and Neptune represent nature's experiment in contrast. They formed side by side over 4.5 billion years ago, in the icy frontier beyond Saturn, from the same swirling cloud of gas and dust that gave birth to the rest of the solar system. Both began as rocky cores, sweeping up surrounding ices and gases until they grew massive enough to hold on to light elements like hydrogen and helium. They are larger than Earth by far, yet too small to become true gas giants like Jupiter or Saturn. The result is a class of planet found nowhere else nearby, neither solid nor gaseous, but something in between. And yet, somewhere in their shared story, their paths diverged. Uranus, pale and even-tempered, seems almost frozen in time. Its atmosphere is calm, its storms faint, its energy barely detectable. Neptune, on the other hand, is alive with motion. Its winds howl faster than any others in the solar system, reaching speeds of over 2,000 kilometers per hour. Vast dark spots appear and disappear across its surface, immense vortices that rise and fade like tempests on a cosmic sea. The same sun that leaves Uranus nearly featureless drives fierce weather on Neptune, though both worlds receive almost the same meagre light. The key difference lies deep within. Neptune radiates more than twice as much energy as it receives from the sun, suggesting that its interior is still warm. Heat left over from its violent formation continues to escape through convection, stirring its atmosphere and feeding its storms. Uranus, by contrast, radiates almost nothing. Its internal heat appears locked away, trapped or lost long ago. Why one twin glows with energy while the other lies dormant remains one of the great mysteries of planetary science. Several theories compete to explain the imbalance. One possibility is that Uranus suffered a massive collision early in its history, the same impact that tilted it onto its side. Such a blow could have disrupted the planet's interior, scattering the layers of ice, rock and gas into a configuration that prevents heat from rising. In effect, Uranus may have sealed itself off, like a flask that can no longer vent steam. Neptune, spared that trauma, kept its structure intact and its inner heat flowing. Another idea suggests that Uranus and Neptune formed in slightly different regions of the early solar system. Perhaps Uranus developed closer to the Sun, where lighter gases were more abundant, while Neptune grew farther out, where heavier ices dominated. When they later migrated to their current positions, these subtle compositional differences may have left one planet better able to retain heat. It's a quiet reminder that even in the emptiness of space, location matters. Small differences at birth can echo across billions of years. Their magnetic fields too reflect their contrasting personalities. Both Uranus and Neptune have magnetic fields that are wildly off-centre, tilted by more than 50 degrees from their rotational axes and displaced from their geometric centres. But Neptune's field, though tilted, behaves with more regularity, while Uranus's seems to wobble unpredictably. These fields are thought to arise from motions within slushy mantles of water, ammonia, and other volatiles, a kind of electrically conductive ice that churns slowly under pressure. On Uranus, that movement appears uneven, perhaps disturbed by the same ancient event that gave it its tilt. On Neptune, the churning continues more steadily, driving a stronger and more stable magnetic rhythm. Even their colours tell part of the story. Uranus shines with a pale pastel blue-green, softened by high-altitude haze that mutes its light. Neptune's deeper blue suggests a clearer atmosphere and perhaps different chemical ratios, more methane or less haze, depending on how sunlight interacts with its gases. Both owe their colour to methane's ability to absorb red light, but Neptune's richness hints at a cleaner sky, one where light penetrates farther before scattering back to space. It's as though Uranus has grown comfortable behind a soft veil, while Neptune has chosen to reveal more of its depth. From a scientific perspective, the study of these two worlds goes beyond simple comparison. Together, they hold the key to understanding an entire class of planets that dominate our galaxy. When astronomers look at exoplanets, worlds orbiting distant stars, they find that the most common type are roughly the size of Uranus and Neptune. These mini-Neptunes, or sub-Neptunes, exist in extraordinary variety. Some are hot and steamy, others cold and dim, some wrapped in thick atmospheres, others with bare icy surfaces. Yet despite their abundance, we know almost nothing about what they're truly like. Our only windows into that category are the two ice giants of our own solar system, one bright and stormy, one muted and still. That's why planetary scientists often speak of Uranus and Neptune as Rosetta Stones for understanding other worlds. If we can decipher their chemistry, their interiors and their evolution, we might begin to understand the patterns that shape planets everywhere. Why do some retain heat while others cool quickly? How does atmospheric composition determine colour and weather? What internal mechanisms sustain magnetic fields in worlds without molten cores? Each question we answer here can illuminate hundreds of systems across the galaxy. The parallels are striking. In exoplanetary surveys, astronomers have found countless examples of worlds that fall between Earth and Neptune in size, too large to be rocky, too small to be gaseous giants. They are worlds with deep atmospheres rich in volatiles orbiting in the temperate zones of their stars. Yet we cannot see them directly. Their light is faint and their features invisible. Uranus and Neptune, sitting quietly at the edge of our own system, are the closest laboratories we have for studying these distant cousins. They are the local representatives of a cosmic majority. The contrast between Uranus and Neptune also teaches humility. Two planets with nearly identical beginnings can evolve in completely different ways, shaped by luck, timing, and chance. One world rolls sideways, its heat buried and its atmosphere subdued. The other spins upright, its energy alive and visible. This difference reminds us that planetary formation isn't a predictable process. It's a symphony of chaos, where small variations can lead to wildly divergent outcomes. In the deeper sense, the twin ice giants illustrate a fundamental balance in nature. Uranus is the stillness, Neptune, the motion. Uranus represents the calm after creation, the cooling of energy into equilibrium. Neptune embodies the lingering fire of youth, the persistence of heat against the cold. Between them lies the full spectrum of planetary temperament, the quiet and the storm, the dormant and the dynamic. Their companionship across billions of years is almost poetic. Locked in neighbouring orbits, they never meet, never collide, but influence each other all the same. Their gravity shapes the paths of countless smaller bodies, icy fragments in the Kuiper belt and the dim outer reaches of the solar system. Together they act as cosmic gatekeepers, marking the transition from the planets we know to the vast, scattered debris that lies beyond. When Voyager 2 visited Uranus in 1986 and Neptune in 1989, the images it sent back captured this duality perfectly. Uranus appeared tranquil, its light uniform and calm. Neptune was dramatic, swirling with bands, storms, and dark spots that seemed to pulse with energy. The photographs looked like portraits of two siblings who had taken an entirely different path through life, one introspective, one expressive. And yet, despite these differences, both share the same fundamental mystery. They are the least explored of all the major planets. The same spacecraft that revealed their beauty has long since moved on, and no probe has yet returned. They wait in the cold, turning slowly under the same distant sun, each guarding its secrets. In the years to come, missions to Uranus, and perhaps later to Neptune, may finally allow us to study these worlds in depth. The data they provide will likely reshape our understanding not just of the solar system, but of planetary systems across the universe. By studying their contrasts, we may uncover the universal principles of planetary evolution, how heat, chemistry, and gravity sculpt worlds from dust and light. For now, Uranus and Neptune remain the twin enigmas of the outer solar system, two planets born from the same cradle, yet destined for different fates. They move together through the dark, silent, but not lifeless, each a reflection of the other's possibilities. Uranus has always stood apart, not because it tries to, but because it must. It rolls through the solar system on its side, a planet turned 98 degrees from the ordinary, forever spinning in a direction that makes no intuitive sense. Every other world twirls upright, presenting their poles neatly to the sun, but Uranus drifts sideways, half in shadow, half in light, as though it refuses to conform. It's an oddity, a quiet rebellion against cosmic symmetry. And in that tilt, there's something profoundly human. Astronomers describe the planet's strange posture in terms of physics. A colossal collision billions of years ago, perhaps with a world the size of Earth, struck Uranus at just the right angle to knock it over. The impact changed everything, its seasons, its magnetism, even the way its moons orbit. What should have been a planet like Neptune became something else entirely. Serene, offbeat, unpredictable. From a distance, Uranus looks peaceful, but its very existence is a testament to chaos. It is balance born from a blow. In that sense, Uranus is not just a planet, it's a story about survival. It reminds us that perfection isn't the natural state of the universe, imbalance is. Stars flare unevenly, galaxies warp, and orbits wobble. Even light bends when space itself curves around gravity. The cosmos is a dance of imperfection, yet it works. Order doesn't emerge from uniformity, it grows out of difference. There's a quiet grace in that idea, that beauty doesn't always stand upright. Uranus embodies it effortlessly. Its tilt makes its seasons last for decades, its poles glow where its equator should, and its rings spin like a sideways crown. What might look broken is, in fact, simply different. A planet in harmony with its own imbalance. When we look at Uranus, we're seeing a cosmic metaphor for how systems, and perhaps people, find equilibrium not by resisting change, but by adapting to it. The planet didn't shatter after its great collision. It redefined itself. Its moons aligned to its new rotation. Its atmosphere settled into its new rhythm. Its magnetic field found a new axis. Even the chaos eventually found calm. There's something deeply philosophical about that. We tend to think of balance as symmetry, as everything in equal measure. But Uranus shows another kind of balance, one that comes from motion, not stillness. It is perpetually off-center, yet stable. Its gravity holds its moons. Its light finds its way through its haze, and its orbit never falters. The tilt that could have been its undoing has become its identity. Perhaps that's why Uranus feels oddly reassuring. In a universe that favours extremes as blazing suns, crushing black holes, violent storms, here is a planet that wears its imperfection quietly. It rolls rather than spins, leans rather than stands, and still it endures. It asks nothing of the viewer except patience, to look past the expectation of normalcy and see the poetry in a symmetry. The physics of its tilt have long fascinated scientists, but the symbolism speaks to something even older, our human desire to make meaning out of misalignment. Throughout history, thinkers have equated order with virtue, straightness with strength. But the universe itself laughs softly at that idea. The orbits of the planets are ellipses, not circles. The Earth's axis wobbles. The Milky Way isn't a perfect spiral. It's lopsided, frayed at the edges. Life itself evolves through mistakes. Creation, it seems, depends on things not going according to plan. Uranus stands as a reminder that asymmetry is not failure, it's design. The same tilt that gives it its strange seasons also creates its beauty. When sunlight skims across its poles, the planet glows in gradients of blue and green unlike any other in the solar system. Its rings, shadowed and brightened in long cycles, trace arcs of light that shift over decades. If Uranus had stayed upright, it might have been ordinary. Instead, it became something serene, singular, and quietly defiant. The human mind isn't so different. We are tilted in our own ways, shaped by moments of impact, by collisions of circumstance and emotion. Each of us carries our own kind of axial tilt, some subtle, some profound. Yet those tilts often become the source of our perspective, the angle through which we see the world differently. The artist, the scientist, the dreamer, all are guided by their unique inclinations, their refusal to spin like everyone else. In a way, Uranus teaches a cosmic form of acceptance. It doesn't fight its tilt or try to right itself. It simply continues, rolling gracefully around the sun, its sideways spin becoming part of its rhythm. That acceptance is what makes it beautiful. Not a resignation to fate, but a quiet confidence in difference. It's easy to forget how much resilience is hidden in that calm exterior. Uranus survived a collision that could have destroyed it. Instead, it became a new kind of planet, one that defied all expectations. Its tilt may have thrown its atmosphere, its interior, and its magnetic field into disarray, yet over billions of years, it found a new equilibrium. Its storms faded into stillness. Its energy settled. It became the most tranquil of worlds, shaped not by avoidance of chaos, but by its graceful aftermath. That's a pattern we see everywhere, from galaxies to people. The ability to find order after upheaval. It's what physicists call dynamic stability, not the absence of motion, but the balance that arises through it. Planets wobble but don't fall. Stars pulsate but endure. Even the solar system itself, with all its gravitational tugs and tilts, remains in a state of cosmic poise. Uranus is the quiet emblem of that truth, a world that leans but never collapses. When sunlight touches Uranus, the glow is faint, scattered by methane and distance, but it persists. A soft turquoise light shines across its clouds, the same light that travels billions of kilometers to reach our telescopes. In that glow is an unspoken lesson. You can exist at the edge of light and still reflect it. There's comfort in imagining the planet as both scientific and symbolic. A frozen giant rolling through space, teaching patience through motion. It reminds us that stillness isn't always possible, and symmetry isn't always ideal. Sometimes, to stay whole, you have to lean. Even its seasons echo this philosophy. For 2 decades, one hemisphere bathes in sunlight while the other lies in darkness, and then slowly they trade places. It's a planetary meditation on fairness. That light always returns, but never perfectly, never all at once. Uranus shows that balance isn't about constancy, it's about rhythm. The world tilts, light shifts, and still the orbit continues. When scientists study Uranus, they often talk about its anomalies, its temperature, its magnetism, its faint heat, its axis. But perhaps the planet's most important feature is not what makes it unusual, but what makes it enduring. It doesn't need to fit the mold of its peers to remain part of the solar system's harmony. It belongs precisely because of its difference. If Uranus could speak, it might say what physics already whispers, that perfection is overrated and stability doesn't require symmetry. A world can lean, wobble, and still be complete. In a universe that prizes light, Uranus reminds us of the quiet power of shade, of the value in subtlety, of finding peace within imbalance. Its tilt isn't a flaw, it's a signature, a record of what it survived and how it continued. At the edge of the solar system, sunlight fades into a kind of memory. It travels for hours before it reaches Uranus, spreading thin and pale, its warmth diluted by distance until it becomes something else entirely, not light that burns, but light that lingers. It touches the planet softly, brushing over the rings, the clouds, the frozen moons, and then drifts onward into the dark. In that quiet space, Uranus keeps rolling, serene and slow, teaching stillness by example. It's a world that seems almost designed for reflection. Every part of it moves on a different clock. Decades-long days, 84-year seasons, centuries of unchanging calm. It has no storms like Jupiter's, No dazzling rings like Saturn's, no volcanic moons or glowing auroras to announce its presence. It asks nothing from the eye except patience. It waits, suspended between light and shadow, content to exist without spectacle. Yet Uranus's story is one of profound motion, of transformation and endurance. From the moment William Herschel first glimpsed it through his telescope in 1781, it expanded the known boundaries of the solar system. That discovery was more than a new planet. It was a reminder that our understanding of the universe is never complete. Herschel's pale green dot, moving slowly across the stars, proved that there was more beyond Saturn's golden rings, that the cosmos continued long after the ancients believed it ended. One night, the sky quietly grew larger. Since then, Uranus has remained a symbol of the unknown, distant, aloof, but deeply instructive. Its sideways spin defies intuition. Its magnetic field bends the rules. Its silence challenges assumptions about what a planet should be. Each of these quirks adds to a broader lesson, that nature is not obliged to conform to our expectations. The universe, like Uranus, tilts in its own direction. The planet's calm exterior hides a history of violence. Billions of years ago, a massive impact, perhaps with a protoplanet the size of Earth, struck Uranus hard enough to knock it over. That single event changed everything, its seasons, its orientation, its energy. What could have been a catastrophe instead became identity. The planet did not break apart. It adapted, rebalanced, and continued. Over time, the chaos faded, and the new order took hold. Its moons fell into the same tilt, its rings adjusted, its axis stabilized. The result is what we see now. A world born from impact, made peaceful by patience. It's tempting to think of that as a kind of cosmic metaphor. Uranus teaches that equilibrium isn't the absence of disturbance, it's the mastery of it. A planet can be struck, scarred, and still move with grace. The same holds true for everything else in the universe. Stars collapsing into stability, galaxies finding balance after collisions, and even the human mind learning to adapt after being tilted off course. Order doesn't come from perfection. It emerges from persistence. That persistence defines Uranus in every sense. It has orbited the Sun countless times since the solar system began, each circuit lasting 84 Earth years. When Voyager 2 flew past in 1986, it caught only the briefest moment of that journey, a few hours of observation in a planetary lifetime. Yet even that short visit changed how we see the outer solar system. Voyager's cameras revealed a world both strange and serene, a pale turquoise sphere, almost featureless, yet mesmerizing in its simplicity. The images of its rings, moons, and magnetic field gave Uranus shape and context, turning what had been an abstraction into a place. And then, just as quietly as it came, the spacecraft moved on, leaving the planet to its silence once more. In the decades since, Uranus has been patient with us. It hasn't changed dramatically, it doesn't demand attention. But telescopes continue to watch, noting the slow shift of light across its poles, the faint storms that appear and fade, the subtle glimmers of methane clouds near its equator. With time, we've come to appreciate its quietness as a kind of wisdom. Where other planets roar with energy, Uranus hums with balance. It is the universe's whisper in a chorus of noise. The planet's colour deepens that impression, that soft turquoise, produced by methane absorbing red light and scattering blue. It's not the electric blue of Neptune or the fiery glow of Mars. It's a gentler tone, something between sky and sea, the colour of calmness itself. Through that hue, Uranus seems to radiate peace. The light that leaves it is faint but pure, sunlight that has travelled billions of kilometres, filtered through a world of ice and reflected back as serenity. There's something quietly philosophical about that light. It reminds us that illumination doesn't always come in intensity. Sometimes it arrives in subtleties, in faintness, reflection, and endurance. The photons that reach us from Uranus have crossed the void not in haste but with patience. They've survived scattering, absorption, and unimaginable distance, yet still carry the story of a tilted world rolling beneath the sun's dim reach. They remind us that even at the edge of sunlight, radiance persists. Every discovery about Uranus, from Herschel's first sighting to Voyager's fleeting visit to the plans for a future orbiter, adds another layer to that story. It's the story of human curiosity reaching outward and time responding inward. We study a planet that moves so slowly that a single season lasts longer than a lifetime. We send machines that pass by in an instant. Between those extremes lies perspective, the contrast between our urgency and the planet's patience. Uranus doesn't hurry because it has no need to. It will complete its orbit long after every spacecraft we've ever launched has gone cold. In that scale, our brief visits seem like flickers against eternity, yet they matter all the same. Perhaps that's the real lesson Uranus offers: perspective. It shows us what endurance looks like in motion. Its tilt, once violent, has become steady. Its silence, once mistaken for emptiness, is full of quiet processes, faint winds, thin hazes, the slow turning of moons in synchrony. Even its distance, once seen as isolation, now feels like poise. Uranus exists not on the outskirts of relevance, but at the centre of reflection. Its moons add to the poetry: Titania, Oberon, Ariel, Umbriel, Miranda, each a fragment of story and structure, orbiting faithfully along the same sideways path. They too lean with their planet, their orbits aligned to its strange geometry. From their surfaces, Uranus would appear immense in the sky, half lit, half shadowed, the ultimate symbol of balance. For 21 years, one pole would shine in daylight, while the other drowned in darkness. A planetary meditation on duality. Eventually the light would shift and the world would roll again. The future holds the promise of another meeting. Plans for a Uranus orbiter and probe aim to return to the planet by the middle of the 2040s, to circle it for years, to dive into its atmosphere, to map its moons and magnetic fields in detail. When that mission finally arrives, it will be more than science. It will be a reunion. After centuries of distance, we will once again listen to the sideways planet and learn from its long quiet. Until then, Uranus remains the watcher, the patient planet, drifting in its measured rhythm. It's easy to forget it's there, hidden in the faint light of the outer solar system, but perhaps that's fitting. Its role is not to dazzle, but to remind. It exists to show that the universe's most powerful lessons often come from its calmest corners. In the vast expanse of space, Uranus glows like an echo of stillness, a world that doesn't seek to impress but to endure. Its rings hum quietly, its moons trace perfect circles in tilted planes, its atmosphere drifts in equilibrium. Everything about it whispers of balance, not in symmetry but in acceptance. It rolls on year after year, century after century, obeying nothing but gravity and grace. It's strange to think how much meaning can be found in such a distant, frozen place, but perhaps that's the essence of astronomy. To look into the dark and find ourselves reflected there. When we study Uranus, we're reminded that even when life turns sideways, motion continues. Even when the light is faint, it still shines. And even when silence seems endless, something beneath it is always moving forward. Uranus keeps rolling, serene and slow, teaching stillness by example. Its tilt, its colour, its calm, all tell the same quiet truth, that there is beauty in imbalance, strength in patience, and peace in simply continuing. And so, in the outer reaches of sunlight, the pale turquoise planet drifts through time. It does not rush, it does not roar, it does not demand to be seen. It only turns, gracefully, endlessly, beneath a faint golden star that still remembers it. Thank you for drifting through the sideways world of Uranus tonight, for journeying through its pale light, its tilted grace, and its quiet defiance of what planets are expected to be. In a universe filled with fire and fury, Uranus reminds us that even in the farthest reaches of cold and distance there is meaning, gentle, subtle, and still. There's something soothing about ending the night with a planet like this one, a world that doesn't shout for attention, that doesn't sparkle with storms or shimmer with heat, but simply rolls through the dark year after year, unchanged and unhurried. It offers a strange comfort, the kind that comes from knowing that not everything needs to blaze to be beautiful. Some things, like Uranus, shine best in quiet. As you close your eyes and let your thoughts settle, you might imagine that distant turquoise globe turning slowly under the sun's weak light. Its rings whisper faint reflections into the dark, its moons follow their sideways paths, and the planet itself hums softly through the silence of space. It doesn't rush, it doesn't demand, it just moves, steady, patient, graceful. It's easy, in the pace of everyday life, to forget what stillness feels like. Our days are crowded with noise and light, full of urgency and expectation, but the universe doesn't share that rhythm. Out there, beyond Mars and Jupiter and Saturn, time stretches differently. Hours become years, seasons last for decades, and movement becomes a kind of meditation. Uranus is the embodiment of that slower tempo, a reminder that time can flow gently and still move forward all the same. In that sense, learning about Uranus isn't just an act of curiosity, it's an act of calm. Science often focuses on discovery, on the thrill of finding something new, but there's another side to it, the quiet joy of understanding something that simply is. To know Uranus is to appreciate subtlety, the soft glow of its colour, the silence of its storms, the way it balances chaos with poise. Its lessons aren't loud, but they last. There's a special kind of peace in knowing that, far away, a planet rolls sideways beneath a dim sun, proof that the universe allows for difference, and that beauty can come from the unexpected. Its tilt, once a sign of disaster, became its defining character. Its cold, once thought of as emptiness, became a symbol of stillness. The story of Uranus is one of endurance and acceptance, of finding grace in imperfection and rhythm in imbalance. If you've followed this journey all the way through, from the discovery by William Herschel to the fleeting visit of Voyager 2, from the icy moons to the promise of future exploration, you've walked in step with both human curiosity and cosmic patience. That pairing, our hunger to learn and the universe's unhurried pace, is what makes astronomy so special. We reach for the stars, but they take their time revealing themselves. Uranus, more than any other world, teaches us to wait. Perhaps that's why its story feels like a bedtime tale written by the cosmos itself. It has all the elements of one: a strange hero, a dramatic past, a quiet resolve, and a gentle rhythm that lulls rather than excites. It reminds us that even in science there's room for stillness, for simply watching and listening. As you settle into rest, imagine the soft turquoise light of Uranus filling the sky above you. Picture its rings like threads of silver smoke, curving gracefully around a world turned on its side. Picture the faint glow reflecting off its moons, each tracing a slow path through shadow and sunlight. There's no rush there, no sound, only the long hum of time itself. And maybe, in that quiet vision, there's something to take with you. Uranus shows that even when life turns sideways, motion continues, that you can be tilted and still balanced, imperfect and still complete. That calm is not the absence of change, but the mastery of it. Its patience is not stagnation, it's peace. Its silence is not emptiness, it's depth. Somewhere, millions of kilometers away, the sunlight that left the sun hours ago is brushing across Uranus's clouds right now. It's faint, almost lost, but still enough to make the planet shine. That same light keeps travelling, scattering through space until it reaches our telescopes, and perhaps, in imagination, reaches you. To think that a beam of sunlight could wander that far and still be seen. It's a small miracle of endurance, and in that way, Uranus reflects something of ourselves. We too are made of endurance. We keep turning through the quiet spaces of our own lives, sometimes upright, sometimes tilted, always moving toward the next patch of light. The planet's long orbit reminds us that progress doesn't always look like motion. Sometimes it looks like grace, the quiet continuation of things, the steady rhythm of simply being. So as this journey draws to a close, let the image of Uranus stay with you. The calm, the colour, the silence. Let it remind you that knowledge can be gentle, that learning can soothe as much as it enlightens, and that even in the vastness of space there are worlds devoted to peace. And if tonight you drift asleep under the same starlit dome that Herschel once watched from his telescope, think of Uranus rolling silently through its endless orbit. Think of how small we are, and how beautiful that smallness becomes when framed by wonder. The planet won't notice our gaze, but it doesn't need to. It already plays its part, a quiet companion to all who seek stillness in a restless universe. Thank you for spending part of your night exploring that stillness, for letting your thoughts wander outward, for listening to a story told in starlight and silence. I hope it brought you a little calm, a little curiosity, and maybe even a touch of awe. May you rest easily now, beneath the same cosmic sky that cradles Uranus and every other world that turns in quiet persistence. The universe is vast, but it's also gentle, and it keeps us all within its rhythm. Sleep well and let the thought linger. Somewhere out there, a pale turquoise world keeps rolling through the dark, serene and slow, forever dreaming beneath the sun's dim reach.